Hello, welcome. I am glad you are here tonight. Wherever you are right now, whatever kind of day you have had, this is your time to rest. This is your invitation to let everything else fall away, gently and completely, like rain sliding off the edge of a leaf. There is no rush. There is nowhere you need to be. There is nothing you need to do right now except breathe and listen. So let us begin with that. Take a slow breath in through your nose. Fill your lungs gently, as though you were drawing in cool evening air, and now let it out, slowly, through your mouth. Let your shoulders drop. Let your jaw relax. Let the weight of the day leave your body like mist evaporating from a warm meadow. Breathe in again, slowly. Feel the air fill your chest, and breathe out. Let everything soften. One more time. Breathe in and breathe out. Good. You are settling now. You are finding your way to stillness. Tonight, we are going to take a long, gentle journey together. We are going to travel through something beautiful and powerful and yet, when understood through the quiet lens of science, remarkably peaceful. We are going to explore the atmospheric chemistry of thunderstorms. Now, when you think of a thunderstorm, you might picture something dramatic, flashes of light, rumbles of sound, rain hammering against windows. And yes, thunderstorms can be intense. But beneath all that spectacle, something extraordinary and quiet is happening. Inside every thunderstorm, there is a hidden world of chemistry. Invisible molecules are meeting. Bonds are forming and breaking. Atoms are rearranging themselves in ways that have shaped our atmosphere for billions of years. And all of it happens in silence, in the spaces between the raindrops, in the heart of the clouds, in the briefest flash of lightning. That is what we are here to explore tonight. Not the drama of storms, but the quiet science within them, the invisible reactions, the gentle chemistry, the slow, patient work of molecules doing what molecules have always done, transforming our atmosphere. One tiny step at a time. We will begin high above the earth, where the air is thin and cool, and we will watch as water vapor rises and clouds begin to form. We will travel inside those clouds and discover the microscopic chemistry happening on the surface of every tiny droplet. We will follow the path of a single lightning bolt and learn how that brief flash of energy creates new molecules that did not exist a moment before. We will drift downward with the rain and feel how each raindrop carries dissolved gases from the sky to the ground. And then, when the storm has passed, we will linger in the calm afterward and listen to the quiet chemistry that continues long after the last rumble of thunder has faded. Along the way, we will meet molecules you may have heard of: oxygen, nitrogen, carbon dioxide, ozone, and some you may not have encountered before: hydroxyl radicals, nitrogen oxides, supercooled water, cloud condensation nuclei. Do not worry about remembering their names. This is not a test. This is a story. A slow, gentle story about the invisible chemistry of the sky. This is a journey designed for rest. The science is real and the details are accurate, but the pace is slow, the language is gentle, and there is no quiz at the end. You are welcome to listen to every word. You are equally welcome to drift off at any point. The storm will still be here if you want to come back. The chemistry will wait for you. So settle in. Let your eyes close if they want to. Let your breathing find its own slow rhythm, and let us begin. Let us start with something simple. What is a thunderstorm? If you were to describe it to a child, you might say it is a big cloud that makes rain and lightning. And that would be true. But if you were to describe it to a chemist, you would say something quite different. You would say that a thunderstorm is a natural chemical reactor. It is a vast, towering laboratory in the sky, where energy from the sun, moisture from the oceans, and invisible gases from the atmosphere all come together to drive thousands of chemical reactions, many of which are essential to life on Earth. That is a remarkable idea, is it not? that the rumbling clouds above your head are, in a sense, performing chemistry, quietly, constantly, on a scale that dwarfs any laboratory ever built by human hands. To understand how this works, we need to begin with the atmosphere itself. The atmosphere is the thin shell of gas that surrounds our planet. It is not very thick, relatively speaking. If the Earth were the size of an apple, the atmosphere would be thinner than the apple's skin, and yet within that thin layer, everything happens. Weather, chemistry, the cycling of elements that keeps our world alive. The atmosphere is divided into layers, stacked one on top of the other like the pages of an enormous, invisible book. The lowest layer, the one closest to the ground, is called the troposphere. This is where we live. This is where weather happens. This is where thunderstorms are born. The troposphere stretches from the ground up to about 10 or 12 kilometers, depending on where you are on the planet and what time of year it is. Near the equator, where the air is warm and buoyant, the troposphere reaches higher. Near the poles, where the air is cold and dense, it is shallower. Above the troposphere sits the stratosphere, a calmer, more stable layer where the air is dry and the winds blow in smooth, horizontal sheets. The stratosphere contains the ozone layer, that thin band of 3-atom oxygen molecules that shields the surface from the sun's most harmful ultraviolet radiation. Thunderstorms are creatures of the troposphere, but the tallest and most powerful ones can punch upward into the lower stratosphere, injecting water vapor and chemicals into that higher, quieter realm. Above the stratosphere lie still more layers, the mesosphere, the thermosphere, the exosphere, each with its own character and chemistry. But these upper layers are far removed from the storms we are discussing tonight. They are quiet, thin, and cold, inhabited by only the rarest of molecules. For our purposes, the troposphere and the lower stratosphere are the stages on which our chemical story will play out. But for now, let us stay close to the ground. Let us think about what the air around us is made of and how it begins its journey upward into the sky. The air you are breathing right now is mostly nitrogen. About 78% of every breath you take is nitrogen gas, a molecule made of 2 nitrogen atoms bonded tightly together. Nitrogen is quiet. It does not react easily. It floats through the atmosphere largely unbothered, a passive observer of the chemical drama happening around it. And yet, as we will see later, lightning has the extraordinary ability to tear nitrogen molecules apart and force them into new chemical combinations. But that comes later. For now, nitrogen simply drifts. The next most abundant gas is oxygen, making up about 21% of the atmosphere. Oxygen is far more reactive than nitrogen. It wants to combine with things. It is the molecule that rusts iron, that feeds fire, that powers the slow combustion happening inside your cells right now as your body converts food into energy. In the atmosphere, oxygen participates in countless chemical reactions, many of which are accelerated and amplified by the energy of thunderstorms. The remaining 1% of the atmosphere is a mixture of other gases. Argon, a noble gas that does essentially nothing chemically, but fills the air with its quiet, inert presence. Carbon dioxide, a trace gas that plays an outsized role in regulating the planet's temperature. Water vapor, the invisible gaseous form of water, whose concentration varies from place to place and from moment to moment, and which is the single most important ingredient in the formation of clouds and storms. Water vapor. Let us pause on this for a moment, because water vapor is the key to everything that follows. Every thunderstorm begins with water vapor. It rises from oceans, lakes, rivers, and damp soil. It evaporates from the leaves of plants in a process called transpiration. It drifts upward from puddles and ponds and wet sidewalks and morning dew. All of this moisture enters the atmosphere as an invisible gas, carried aloft by warm, rising air. And here is where the chemistry begins. As water vapor rises, it encounters cooler temperatures. The higher you go in the troposphere, the cooler the air becomes. This cooling is predictable and steady, dropping by roughly 6.5 degrees Celsius for every kilometer of altitude. This rate of decrease is called the environmental lapse rate, and it is one of the fundamental facts of atmospheric science. As the air cools, it can hold less and less water vapor. There is a limit to how much invisible moisture the air can contain at any given temperature, and that limit decreases as the temperature drops. Eventually, the rising air reaches a point where it is holding all the water vapor it can possibly contain. It has reached its dew point. It has become saturated. It can hold no more moisture in its gaseous form. And at that moment, something beautiful happens. The water vapor begins to condense. It begins to transform from an invisible gas into tiny, visible droplets of liquid water. It begins to form a cloud. Condensation, the transition from gas to liquid, from invisible to visible, from empty air to the first faint wisps of a cloud. But condensation does not happen in a vacuum. Water vapor does not simply decide on its own to become a droplet. It needs a surface to condense onto. It needs a tiny particle, a speck of something solid, floating in the air, onto which the first molecules of liquid water can gather. These particles are called condensation nuclei, or more specifically, cloud condensation nuclei. Cloud condensation nuclei are everywhere in the atmosphere. They are particles of sea salt, lifted from the ocean surface by breaking waves and the bursting of tiny bubbles in the sea foam. They are grains of dust, carried aloft by wind from deserts and dry fields and construction sites. They are specks of pollen, fragments of volcanic ash, and tiny droplets of sulfuric acid formed from the oxidation of sulfur gases emitted by volcanoes and by industrial activity. They are particles of soot and smoke from forest fires and the burning of fossil fuels. They are even biological particles, fragments of bacteria, spores of fungi, and tiny pieces of plant material carried into the atmosphere by the wind. These particles are incredibly small, typically just a fraction of a micrometer in diameter. You cannot see them, you cannot feel them, but they are there, floating in the air by the billions, waiting to serve as scaffolding for cloud droplets. Without them, clouds could not form. Water vapor, no matter how saturated the air became, would have nothing to condense onto. The sky would remain clear, and rain would never fall. It is one of those quietly underappreciated facts of nature. The existence of clouds depends on the existence of tiny, invisible particles of dust and salt and sulfate and smoke. When water vapor condenses onto a cloud condensation nucleus, it forms a tiny droplet. This droplet is extraordinarily small, perhaps 10 to 20 micrometers in diameter. For comparison, a human hair is roughly 70 micrometers wide, so a cloud droplet is less than a third the width of a hair. These cloud droplets are so small and so light that they float in the air, suspended by the gentle updrafts and turbulent motions within the cloud. They do not fall. They are too small to overcome the resistance of the air. They simply float, drifting with the wind, bumping gently into their neighbors, slowly growing or shrinking as conditions change. A single cloud may contain billions upon billions of these droplets, each one a microscopic sphere of water clinging to a tiny particle of dust or salt or sulfate. And each one of those droplets is, in its own tiny way, a chemical reactor. On the surface of each droplet and within the liquid water itself, chemical reactions are taking place. Gases from the surrounding air dissolve into the water. Acids form. Ions are released. Oxidation reactions occur. The chemistry of the cloud is alive and active, even though it looks, from the ground, like nothing more than a soft, white mass drifting across the sky. But we are getting ahead of ourselves. let us slow down, let us return to the rising air. The process that lifts air upward and creates the conditions for cloud formation is called convection. Convection is driven by the sun. When sunlight falls on the Earth's surface, it warms the ground. Different surfaces absorb heat at different rates. A dark parking lot absorbs more heat than a grassy field. A plowed field absorbs more heat than a forest canopy. A sandy beach absorbs heat differently than the ocean beside it. These differences create pockets of air near the surface that are warmer than the air around them. Warm air is less dense than cool air. It is lighter, in a sense, though what we really mean is that it occupies more volume per unit of mass. And so, it begins to rise, like a bubble in a pot of slowly warming water. These rising bubbles of warm air are called thermals, and on a warm summer day, they are everywhere, lifting invisibly from heated surfaces and carrying their cargo of warmth and moisture upward into the atmosphere. As this warm air rises, it expands. It expands because the pressure of the atmosphere decreases with altitude. There is less air above pressing down, so the rising parcel of air can spread out. And as it expands, it cools. This is not because anything is taking heat away from it. It is simply the physics of expanding gas. When a gas expands without exchanging heat with its surroundings, its temperature drops. This is called adiabatic cooling, and it is one of the most important processes in atmospheric science. It is the reason that mountains are cold, that airplane cabins need to be pressurized and heated, and that the tops of thunderstorm clouds are made of ice. The rising, cooling air carries its water vapor upward. As it cools, it approaches the dew point, and when it reaches the dew point, condensation begins. Clouds form, and as condensation occurs, something interesting and important happens. The process of condensation releases heat. It releases the same energy that was absorbed when the water evaporated from the surface in the first place. This energy is called latent heat, and it is a significant source of energy within a developing storm cloud. The release of latent heat warms the air inside the cloud, making it even more buoyant than the surrounding air. This increased buoyancy causes the air to rise even faster, which lifts more moisture to higher altitudes, which leads to more condensation, which releases more latent heat, which drives the air higher still. This is a positive feedback loop, and it is the engine that powers a thunderstorm. The cycle of rising air, condensation, heat release, and further rising can build a cloud from a humble cumulus puff into a towering cumulonimbus, a cloud that stretches from near the surface all the way to the top of the troposphere, sometimes reaching heights of 15 kilometers or more. These are the clouds of thunderstorms. These are the chemical reactors we came here to study. But let us not rush. The cloud is still growing. The chemistry is just beginning. And there is so much more to discover, gently, slowly, as we drift deeper into the quiet science of storm clouds. Think of the temperature gradients within this rising column of air. At the base of the cloud, the temperature might be a comfortable 15 degrees Celsius. But at the top, where the cloud has mushroomed outward into the familiar anvil shape of a mature cumulonimbus, the temperature has plummeted to minus 50 or 60 degrees Celsius. This enormous range of temperatures means that the cloud contains water in multiple states simultaneously. Near the base, there are liquid water droplets. In the middle, there is a mixture of liquid water and ice. At the very top, there are only ice crystals, tiny hexagonal plates and needles of frozen water glinting in the high-altitude sunlight. The coexistence of liquid water and ice within the same cloud is not just a curiosity. It is fundamental to the physics and chemistry of the storm. The interaction between water droplets and ice crystals drives the growth of precipitation. It generates the electrical charges that produce lightning. And it creates a range of chemical environments, warm and wet, cold and icy, and everything in between that allow different chemical reactions to proceed simultaneously in different parts of the cloud. Supercooled water is a particularly fascinating substance. It is water that has cooled below the freezing point below 0 degrees Celsius and yet has not frozen. It remains liquid, in a state of delicate, unstable suspension, waiting for the slightest disturbance to trigger the formation of ice. In the interior of a thunderstorm cloud, supercooled water droplets can exist at temperatures as low as -30 or even -40 degrees Celsius. They persist because the formation of ice requires a nucleation site, a tiny particle or surface on which the first ice crystal can begin to grow, and not every droplet contains a suitable nucleation site. When ice does finally form, it often happens suddenly. A single ice crystal appears, and then, in a cascade, surrounding supercooled droplets freeze almost simultaneously, triggered by the ice crystal's presence. The release of latent heat during this freezing can produce a small, localized burst of warming within the cloud, altering the dynamics and chemistry of the immediate area. And when ice forms, it changes the chemistry of the cloud dramatically. Ice crystals grow at the expense of surrounding liquid droplets in a process known as the Bergeron process or the Wegener-Bergeron-Findyson process. The saturation vapor pressure over ice is lower than over liquid water at the same temperature. This means that in a mixture of ice crystals and supercooled water droplets, the air is supersaturated with respect to ice, but unsaturated or merely saturated with respect to liquid. The ice crystals pull water vapor away from nearby droplets, causing the droplets to evaporate while the crystals grow larger. This process is central to the formation of precipitation in many types of clouds, and it also influences the distribution of dissolved chemicals within the cloud, as the evaporating droplets release their dissolved gases and the growing ice crystals exclude many dissolved substances. All of this, the rising air, the condensation, the supercooled droplets, the ice crystals, the latent heat, the temperature gradients, the aerosols and nuclei, all of this is happening inside a storm cloud, and every bit of it involves chemistry. The chemistry of phase transitions as water moves between gas, liquid, and solid. The chemistry of dissolved gases as atmospheric compounds enter and leave the liquid phase. The chemistry of surfaces and interfaces, where reactions occur on the boundaries between air and water, water and ice, and air and the surfaces of tiny particles. The chemistry of energy, as heat is released and absorbed, driving the motions that stir and mix the cloud's chemical contents. And yet, from the ground, it simply looks like a cloud. A dark, beautiful, slowly shifting mass of gray and white and purple, moving across the sky, quietly, patiently, doing its ancient chemical work. Take a breath. Let yourself settle a little deeper into wherever you are resting. The storm cloud is growing above us, and there is no hurry. The chemistry will continue at its own pace, and so shall we. Let us linger here a moment longer. Imagine yourself standing outside on a summer evening, watching that cumulonimbus grow on the horizon. The base of the cloud is dark, almost charcoal gray, because it is so thick that very little sunlight penetrates through it. The water droplets and ice crystals inside the cloud scatter and absorb the light, creating that deep, moody darkness that signals rain. But the top of the cloud, towering above, is still catching the light of the setting sun. It glows brilliant white and gold, and sometimes pink, its upper surface sculpted by the wind into smooth, fibrous textures. The contrast between the dark base and the illuminated top is one of the most beautiful sights in nature. Inside that cloud, the air is in constant vertical motion. The updraft, the central column of rising air, may be moving upward at 20, 30, even 50 meters per second in a strong storm. That is faster than most elevators. Air that was near the ground just minutes ago is now at the top of the troposphere, its temperature having dropped by 60 or 70 degrees. its water vapor having condensed into billions of droplets and ice crystals, its chemical cargo having been transported from the warm, polluted boundary layer to the cold, clean upper atmosphere. Alongside the updraft, there are downdraft's columns of air sinking from the middle and upper levels of the cloud. These downdrafts are driven by the evaporation and melting of precipitation. When rain falls from a cloud into drier air below, some of the raindrops evaporate. This evaporation absorbs heat from the surrounding air, cooling it. The cooled air becomes denser than its surroundings and begins to sink. It accelerates downward, dragging more air with it, picking up speed as it descends. When it reaches the ground, it spreads outward as a gust of cool wind, the refreshing burst of cold air that often precedes a thunderstorm. This interplay of updrafts and downdrafts creates the characteristic turbulence inside a thunderstorm. If you have ever flown through a thunderstorm in an airplane or imagined doing so, you know that the air inside is anything but calm. Pockets of rising air alternate with pockets of sinking air, creating sudden bumps and jolts. But from the outside, from our quiet vantage point on the ground, all of this internal turbulence is hidden. We see only the stately cloud, growing and shifting, its movements so slow and so large that they seem almost geological. And within that turbulence, chemistry is happening everywhere. Every time two parcels of air mix, warm with cold, moist with dry, polluted with clean, the chemical composition of the resulting mixture is different from either of its parents. New reactions become possible. New products form. The turbulent mixing inside the cloud is not just a physical process. It is a chemical process as well, constantly creating new combinations of reactants, constantly driving the chemistry forward. Now that we have watched a cloud begin to form, let us take a step back and think more deeply about the air itself. The atmosphere is not just a container for weather. It is a vast, dynamic chemical system, a reservoir of molecules that interact with each other in complex and beautiful ways. Every gas within it plays a role. Some of those roles are large and obvious. Others are subtle and slow. But all of them matter, especially during a thunderstorm, when the energy of the storm stirs the atmosphere's chemistry into heightened activity. Let us walk through these invisible ingredients, one by one, slowly and carefully. There is no rush. Each molecule has its own story, its own personality, its own quiet contribution to the chemistry of the sky. Let us begin with nitrogen. Nitrogen gas, which scientists write as NO2, is the most abundant molecule in the atmosphere, making up about 78% of the air by volume. It is a simple molecule, just two atoms of nitrogen bound together, but the bond between them is extraordinary. It is a triple bond, one of the strongest chemical bonds in all of nature. 3 pairs of electrons are shared between the 2 nitrogen atoms, binding them together with a force that very few natural processes can overcome. This triple bond is what makes nitrogen so stable, so reluctant to react with other molecules. Under normal atmospheric conditions, nitrogen gas is almost inert. It passes through your lungs with every breath and exits unchanged. It drifts through the atmosphere for millions of years without reacting. It does not combine with oxygen. It does not dissolve significantly in water. It does not participate in the everyday chemistry of the lower atmosphere. It is the quiet backbone of the air, the still water beneath the surface. And yet, nitrogen is essential to life. Every protein in your body contains nitrogen. Every strand of DNA, every molecule of chlorophyll in every green leaf, every amino acid, every neurotransmitter carrying a signal through your brain right now. The nitrogen cycle, the set of processes by which nitrogen moves from the atmosphere into living things and back again, is one of the most important chemical cycles on Earth. And one of the most remarkable steps in that cycle, as we shall discover later, occurs inside a thunderstorm when lightning tears nitrogen molecules apart and forces them into reactive new forms that living things can use. But for now, nitrogen is simply floating, quietly, abundantly, making up more than 3/4 of every cubic meter of air. Next comes oxygen. Oxygen gas, O2, is the second most abundant molecule in the atmosphere, making up about 21% by volume. Unlike nitrogen, oxygen is reactive. It is eager to combine with other elements. It is the molecule that makes fire possible, because combustion is simply the rapid reaction of a fuel with oxygen. It is the molecule that drives respiration, the slow, controlled combustion that powers nearly every animal and most microorganisms on Earth. In the atmosphere, oxygen participates in a vast web of chemical reactions. It combines with metals to form oxides. It reacts with organic compounds emitted by plants and by human activity. It interacts with ultraviolet light from the sun to create ozone, a molecule we will discuss in great detail later. And during thunderstorms, it is swept into high-energy reactions driven by the immense temperatures of lightning, producing new compounds that ripple through the atmospheric chemical system. Oxygen also has a quieter, more subtle role. In the atmosphere, individual oxygen atoms, freed from their molecular partners by ultraviolet radiation or by chemical reactions, become highly reactive species known as oxygen radicals. These radicals are short-lived but enormously important. They are the spark plugs of atmospheric chemistry, the tiny initiators that ignite chains of reactions capable of transforming pollutants, creating new molecules, and regulating the composition of the air we breathe. We will meet these radicals many times throughout our journey tonight. Argon is the third most abundant gas in the atmosphere, making up nearly 1% by volume. Argon is a noble gas. Its electron shells are full, perfectly satisfied, and it has no chemical desire to react with anything. It simply exists in the atmosphere, a peaceful, inert observer, like a meditator sitting quietly in a busy marketplace. Argon was formed deep in the Earth's crust, produced by the radioactive decay of an isotope of potassium 40 over billions of years. It seeped slowly through the rock and soil and into the atmosphere, accumulating over geological time until it reached its current concentration. Argon does nothing chemically in the atmosphere. It does not react. It does not condense. It does not participate in any of the chemical cycles we will discuss. But its presence is a gentle reminder that the atmosphere is not just a product of life and weather. It is also a product of deep geological processes happening far beneath our feet on timescales that dwarf human experience. Now let us consider carbon dioxide. Carbon dioxide, CO2, makes up a small fraction of the atmosphere, roughly 420 parts per million, or about 0.04%. Despite its low concentration, carbon dioxide is one of the most important gases in the atmosphere. It absorbs infrared radiation emitted by the Earth's surface and re-emits it in all directions, trapping heat and warming the planet. This is the greenhouse effect, and carbon dioxide is one of its primary drivers. Without the greenhouse effect, the Earth's average surface temperature would be roughly 33 degrees Celsius colder than it is today, and the planet would be a frozen, lifeless ball of ice. Carbon dioxide enters the atmosphere from many sources. Volcanoes release it from deep within the Earth. Animals exhale it as a byproduct of respiration. Fires release it as organic matter burns. And human activities, the burning of fossil fuels, the clearing of forests, the manufacture of cement release enormous quantities of it, far more than natural processes can absorb. The rising concentration of carbon dioxide in the atmosphere is the primary driver of the global climate change occurring today. During thunderstorms, carbon dioxide plays a quiet role. It dissolves into raindrops, forming a weak acid called carbonic acid. This process, as simple as it sounds, is one of the ways the atmosphere slowly weathers rocks and recycles carbon through the Earth system. We will explore this more when we discuss the chemical life of rain. Methane is even less abundant than carbon dioxide, present in the atmosphere at concentrations of roughly 1,900 parts per billion, or about 2 parts per million. But molecule for molecule, methane is a far more potent greenhouse gas than carbon dioxide, trapping roughly 80 times as much heat per molecule over a 20-year period. Methane is produced by wetlands, where bacteria break down organic matter in the absence of oxygen. It is produced by agriculture, particularly by rice paddies, and by the digestive systems of ruminant animals like cows and sheep. It is released from the slow decay of organic matter in landfills, and it seeps from natural gas deposits and thawing permafrost in the Arctic. In the atmosphere, methane is gradually broken down by reactions with hydroxyl radicals, those reactive fragments of water molecules that serve as the atmosphere's primary cleaning agent. This is a slow process, and the average methane molecule survives in the atmosphere for roughly 12 years before being oxidized. Thunderstorms play a role in this process, both by producing the hydroxyl radicals that destroy methane and by transporting methane-rich air from the surface into the upper atmosphere, where different chemical pathways operate and where methane can have different effects on atmospheric chemistry. Let us turn now to ozone. Ozone is a molecule of 3 oxygen atoms, written as O3, and it exists in 2 very different parts of the atmosphere with 2 very different roles. In the stratosphere, high above the weather, between about 15 and 35 kilometers in altitude, ozone forms a protective layer that absorbs ultraviolet radiation from the sun. This ultraviolet radiation, particularly the high-energy UVB and UVC wavelengths, is harmful to living organisms. It can damage DNA, cause skin cancer, and harm the cells of plants and animals. The stratospheric ozone layer absorbs most of this harmful radiation before it reaches the surface, acting as a planetary sunscreen. This is the so-called good ozone, the ozone that protects life on Earth. But ozone also exists in the troposphere, at ground level, where it is a pollutant and a health hazard. Tropospheric ozone is produced by chemical reactions involving nitrogen oxides and volatile organic compounds in the presence of sunlight. In high concentrations, it irritates the respiratory system, damages crops, and reduces visibility. This ground-level ozone is sometimes called bad ozone. Though the molecule itself is exactly the same, it is only its location that makes it helpful or harmful. Thunderstorms influence ozone chemistry in complex and interconnected ways. They produce the nitrogen oxides that contribute to ozone formation. They generate the vertical mixing that transports ozone and its precursors between different layers of the atmosphere. They produce the hydroxyl radicals that participate in ozone destruction cycles. And the lightning itself directly produces small amounts of ozone in the immediate vicinity of the discharge. We will explore all of these connections in a later section. And then there is water vapor. We spoke about water vapor earlier when we discussed cloud formation, but it deserves deeper attention because in many ways, water vapor is the most important gas in the atmosphere. Water vapor is the most variable gas in the atmosphere. Its concentration changes constantly, from place to place and from moment to moment. In dry desert air, far from any source of moisture, water vapor may make up less than 0.5% of the air by volume. In warm, humid tropical air, over a warm ocean or a lush rainforest, it can make up as much as 4%. This variability is important because water vapor is not just the raw material for clouds and rain. It is also the single most powerful greenhouse gas in the atmosphere, responsible for a larger share of the greenhouse effect than carbon dioxide, methane, or any other gas. And it is the precursor to the hydroxyl radical, the most important oxidizing agent in the troposphere. When ultraviolet light from the sun strikes a molecule of ozone in the troposphere, it can break the ozone into an oxygen molecule and a single excited oxygen atom. This excited oxygen atom vibrating with excess energy, can then react with a nearby water vapor molecule, splitting it into two hydroxyl radicals. These hydroxyl radicals, each one just a single oxygen atom bonded to a single hydrogen atom, are extraordinarily reactive. They immediately begin to react with whatever other molecules they encounter, whether methane, carbon monoxide, volatile organic compounds, or nitrogen oxides. Through these reactions, the hydroxyl radical breaks down pollutants and greenhouse gases, cleaning the atmosphere one molecule at a time. Thunderstorms enhance the production of hydroxyl radicals in several ways. They loft water vapor to high altitudes, where it can encounter the ultraviolet radiation needed to drive the photolysis reactions. They produce nitrogen oxides, which participate in the catalytic cycles that regenerate hydroxyl radicals from their reaction products. And they create the turbulent mixing that brings water vapor, ozone, and ultraviolet light together in the right proportions and at the right altitudes. There are other trace gases in the atmosphere, too many to name them all tonight, but a few are worth mentioning because of their roles in the chemistry of thunderstorms. Sulfur dioxide, emitted by volcanoes and by the burning of sulfur-containing fossil fuels, dissolves in cloud water to form sulfurous acid and can be further oxidized to sulfuric acid, a major component of acid rain. Ammonia, released from agricultural activities, livestock waste, and natural biological processes in soils, also dissolves in cloud water and partially neutralizes the acids present, forming ammonium salts. Volatile organic compounds, emitted in vast quantities by forests as well as by human activities, undergo complex chemical transformations in the atmosphere, producing secondary organic aerosols that can serve as cloud condensation nuclei and influence the properties of clouds and storms. And there are the atmospheric radicals, those highly reactive, short-lived molecular fragments that drive the chemistry of the troposphere like tiny, tireless workers. The hydroxyl radical, O, is the most important, but there are others. The hydroperoxyl radical, O2, a close relative that serves as a reservoir of reactive hydrogen. The nitrate radical, NO3, which operates primarily at night, in the darkness after storms have passed, oxidizing organic compounds under the cover of darkness. Organic radicals, fragments of broken down hydrocarbons that participate in the complex photochemistry of the sunlit atmosphere, linking the chemistry of natural emissions and human pollution into a single, intricate web. All of these molecules, from the abundant nitrogen and oxygen to the trace gases and fleeting radicals, are the ingredients of atmospheric chemistry. They are the raw materials that thunderstorms work with. They are the characters in the chemical story we are telling tonight. And as we move deeper into the storm, we will see how these ingredients are mixed, heated, torn apart, recombined, and redistributed by the enormous energy of the storm. But there is no hurry. The molecules are patient. They have been doing this work for billions of years, since the Earth first had an atmosphere, since the first thunderstorm rumbled across a young and lifeless world. A few more minutes of quiet contemplation will not change anything. So, breathe slowly. Let your mind drift among the molecules. Imagine them floating around you in the dark, invisible, gentle, endlessly in motion. And let us continue, softly, into the next chapter of our story. Every thunderstorm begins with the sun. It begins with sunlight falling on the surface of the earth, warming the ground, warming the water, warming the air. The sun is the engine of all weather, the source of all the energy that drives the circulation of the atmosphere and the cycling of water between the earth and the sky. And the thunderstorm is one of the sun's most powerful and beautiful creations. Imagine a warm summer morning. The sun has been shining for a few hours. The ground is heating up. Over a dark plowed field, the air near the surface is becoming warmer than the air above it. This pocket of warm air is lighter than the cooler air surrounding it. It is buoyant, and so Gently at first, it begins to rise. Not quickly, not violently, just a gentle, easy upward motion, like a balloon released from a child's hand, drifting slowly into the sky. This rising motion is the first step in the birth of a thunderstorm. It is convection, the transfer of heat by the physical movement of a fluid, in this case, air, and it is driven by instability in the atmosphere. When the temperature of the air decreases rapidly with altitude, more rapidly than the rate at which a rising parcel of air cools, the atmosphere is said to be unstable. In an unstable atmosphere, a parcel of air that begins to rise will continue to rise because it remains warmer and therefore lighter than the air around it. It accelerates upward, gathering speed and moisture as it climbs. The conditions for instability can arise in many ways. Strong solar heating of the surface on a summer afternoon is the most common, but instability can also be created by the arrival of a cold front, a boundary where cool, dense air pushes underneath warm, moist air, lifting it upward. It can be created by the convergence of wind patterns, where air from different directions meets and has nowhere to go but up. It can be enhanced by the terrain. Mountains and hills force air to rise as it flows over them, and the heating of mountain slopes creates upslope winds that carry moisture to higher altitudes. Whatever the cause, the result is the same. A parcel of warm, moist air begins to rise through the atmosphere. As it rises, it cools adiabatically. It cools at a rate of roughly 10 degrees Celsius per kilometer if the air is unsaturated, meaning it has not yet reached its dew point and condensation has not yet begun. This is called the dry adiabatic lapse rate, and it is a constant of atmospheric physics, a consequence of the relationship between pressure, volume, and temperature in an ideal gas. But once the rising air reaches the altitude where its temperature equals the dew point, a level known as the lifting condensation level, condensation begins. Cloud droplets start to form, and the latent heat that comes out of condensation slows down the cooling process. Now the air cools at the saturated adiabatic lapse rate, which is typically around 5 to 6 degrees Celsius per kilometer. This is slower than the dry rate because the latent heat is partially offsetting the cooling caused by expansion. This is a crucial detail, and it is worth lingering on for a moment, because it is the key to understanding how thunderstorms grow. Once a cloud begins to form, the rising air cools more slowly than it would if no condensation were occurring. And because it cools more slowly, it remains warmer relative to its surroundings. It remains more buoyant. It continues to accelerate upward, and as it rises, more water vapor condenses, releasing more heat, reducing the cooling rate further, making the air even more buoyant. The cloud grows. It billows upward, a great white tower of condensing moisture and released energy, climbing higher and higher into the atmosphere. In the early stages, the cloud is a cumulus, a fair-weather cloud with a flat base and a billowing, cauliflower-like top. It is pretty and harmless, the kind of cloud that decorates summer afternoons and inspires daydreams. But if the atmosphere is sufficiently unstable, and if there is enough moisture in the air, the cumulus cloud continues to grow. Its top reaches higher. It encounters colder temperatures. Ice begins to form within it. The cloud becomes taller, wider, darker, more imposing. Its base broadens and deepens, heavy with moisture. And then something remarkable happens. The cloud's top, climbing through ever colder air, reaches the tropopause, the boundary between the troposphere and the stratosphere. The tropopause is a temperature inversion, a region where the temperature stops decreasing with altitude and begins to increase. This stable layer acts as a lid, a ceiling that resists the upward push of the rising cloud. When the cloud reaches this ceiling, it can no longer rise. Instead, it spreads outward horizontally, forming the distinctive anvil shape that is the hallmark of a mature cumulonimbus cloud. The anvil, made of ice crystals blown outward by the high-altitude winds, can spread for dozens or even hundreds of kilometers downwind of the storm, a wispy, luminous extension of the great dark tower beneath it. And now we have a thunderstorm, a fully developed cumulonimbus cloud, stretching from perhaps 1 or 2 kilometers above the surface to 12 or 15 kilometers in altitude. Inside this cloud, the air is in constant motion, with updrafts carrying warm, moist air upward at speeds of 30 or 40 meters per second, and downdrafts carrying cool, dry air downward from the middle and upper levels. The cloud contains liquid water, supercooled water, ice crystals, graupel particles, and sometimes even hail. It is a churning, dynamic, three-dimensional structure, constantly evolving, constantly rearranging itself. But from a distance, from our quiet place of rest, the cloud simply looks majestic. A great, dark tower rising into the sky, its anvil top catching the last light of the sun, its base heavy and dark with rain, a distant rumble of thunder reaching our ears, soft and low, like the purring of some vast, gentle creature. Let us think about what is happening chemically during this process of storm development. The rising updraft is not just carrying water vapor upward. It is carrying all the gases and particles that were present near the surface: nitrogen, oxygen, carbon dioxide, methane, pollutants, nitrogen oxides from traffic, sulfur dioxide from industry, volatile organic compounds from vehicle exhaust and solvents and industrial processes, natural emissions, isoprene and terpenes from forests, dimethyl sulfide from the ocean, ammonia from soils and agriculture, dust particles, pollen grains, sea salt crystals, soot from fires. All of these substances are being swept up by the updraft and transported vertically through the atmosphere, from the surface to the upper troposphere, in a matter of minutes. This vertical transport is one of the most important chemical functions of a thunderstorm. It is sometimes called convective venting, and it is a primary mechanism by which the composition of the upper troposphere is influenced by emissions at the surface. Under normal conditions, the mixing of air between the surface and the upper atmosphere is slow, occurring over days or weeks through the gradual action of turbulence and diffusion. Pollutants and reactive gases tend to accumulate near the ground, where they were emitted, trapped in the atmospheric boundary layer by a temperature inversion that prevents vertical mixing. But a thunderstorm punches through that inversion like a fist through a paper ceiling, sucking air from the surface and injecting it into the upper troposphere in a matter of an hour or less. This rapid redistribution of chemicals has profound effects on atmospheric chemistry. Gases that are relatively unreactive at ground level, where they are surrounded by other pollutants and where photochemical conditions are one way, may find themselves in a very different environment at 12 kilometers altitude. The air up there is cleaner, colder, and drier. The ultraviolet radiation is more intense because there is less atmosphere above to absorb it. The chemical lifetimes of reactive species can be very different, and the products of chemical reactions at high altitude can be transported by the winds over enormous distances, spreading the chemical influence of a single thunderstorm across an entire continent or even an ocean. Consider nitrogen oxides as an example. At the surface, nitrogen oxides are produced mainly by combustion from car engines, power plants, and fires. They are reactive, and they participate in the photochemical smog cycle that produces ozone in polluted urban areas. But their effects are largely local, confined to the region around their source. When a thunderstorm lifts these nitrogen oxides to the upper troposphere, they encounter a different chemical landscape entirely. The air is cleaner. The ozone production efficiency is higher because there are fewer competing reactions. And the ozone produced in the upper troposphere has a longer lifetime and a greater radiative impact than ozone near the surface. So, the simple act of vertical transport lifting pollution from the ground to the sky amplifies the chemical and climatic effects of those pollutants. And then there is the lightning itself, which produces its own nitrogen oxides entirely independently of any surface pollution, but we will come to that in the next section. For now, let us simply appreciate the convective engine of the thunderstorm, the way it stirs the atmosphere like a giant spoon stirring a vast pot of invisible chemicals, mixing layers that would otherwise remain separate, bringing substances into contact that would otherwise never meet, and setting the stage for the chemical reactions to come. The pressure gradients within the storm drive this mixing in complex ways. As the warm air rises in the updraft, it creates a region of lower pressure near the surface, which draws in more air from the surrounding environment. This inflow of air, sometimes called the storm's inflow, brings additional moisture and chemicals into the base of the storm, feeding the updraft and intensifying the convection. Meanwhile, at the top of the cloud, the outflowing air carries its chemical cargo away from the storm. The anvil outflow spreads horizontally, distributing processed air that has been lifted, cooled, condensed, and chemically altered by the cloud over a wide area of the upper atmosphere. And throughout all of this, the air inside the cloud is being mixed by turbulence on all scales. Large-scale circulations carry air from the base to the top and back again. Smaller eddies, rotating at many different scales, churn the air within the cloud, blending warm and cold air, moist and dry air, polluted and clean air, into a complex, ever-changing mixture. This turbulent mixing is what brings different chemical species into contact with each other, creating the conditions for the countless reactions that occur within the storm. From our quiet place of rest, we cannot see any of this. We see only the cloud, growing slowly against the sky, its top reaching upward, its base darkening with rain. We hear the first distant rumble of thunder, a sound that tells us that somewhere inside that cloud, the electrical field has grown strong enough to produce lightning. The storm is maturing. The chemistry is intensifying, but there is no urgency. The storm will take its time, and so shall we. Let us also pause to consider the fate of the molecules that are not directly involved in the dramatic chemistry of lightning and ozone production. Consider, for instance, the molecules of perfume from a garden of flowers, lifted from the warm surface and carried upward by the storm's inflow. These volatile organic compounds, esters and terpenes and aldehydes, are swept into the updraft and carried to altitudes where they have never been before. At those altitudes, they encounter stronger ultraviolet radiation, lower temperatures, and different concentrations of oxidants. Some of them are oxidized by the hydroxyl radical and broken down into simpler molecules. Others condense onto existing particles, contributing to the organic coating that surrounds many atmospheric aerosols. A few, perhaps, survive the journey and are expelled from the top of the storm in the anvil outflow, traveling hundreds of kilometers downwind before finally being destroyed or deposited. Or consider the microorganisms. Yes, the atmosphere contains microorganisms, bacteria, fungal spores, and even viruses that are swept up from the surface by the wind and carried aloft. Some of these microorganisms can survive for extended periods in the atmosphere, drifting in the clouds, perhaps even metabolizing the dissolved organic compounds in cloud droplets. Thunderstorms lift these microorganisms to high altitudes and transport them over great distances. There is evidence that viable bacteria can be found in cloud water at altitudes of several kilometers, and that they may even play a role in cloud chemistry by catalyzing certain reactions or by serving as ice nucleating particles that promote the formation of ice crystals. The idea that living organisms participate in the chemistry of clouds is a relatively new one, and it is still being explored. But it is a beautiful thought that the chemistry of a thunderstorm is not just the work of atoms and molecules, but also, in a small way, the work of life itself. The atmosphere is not a sterile, purely chemical environment. It is a living system, inhabited by microorganisms that interact with the chemistry around them, influencing cloud formation, precipitation, and the cycling of nutrients. The boundary between atmospheric chemistry and biology is not as sharp as we might imagine. Think about that as you rest. The air around you is alive, in a very literal sense. Billions of microorganisms are floating in it right now, on the dust particles, in the water vapor, in the invisible currents that drift past your face. They are doing nothing dramatic. They are simply existing, carried by the wind, waiting for the next rain to bring them back to Earth. They are part of the atmospheric system, just as the nitrogen and the oxygen and the ozone are. Part of the vast, quiet, interconnected web of chemistry and life that makes our atmosphere what it is. And during a thunderstorm, all of these elements, the gases, the particles, the microorganisms, the water, the energy, are brought together in a single, extraordinary event. The storm is a gathering, a convergence, a moment when the scattered ingredients of the atmosphere are concentrated and mixed and energized and transformed. And when the storm passes, those ingredients are scattered again, dispersed across the sky, subtly changed, ready for the next gathering. It is a rhythm as old as the planet, as regular as breathing, as gentle as the rain. Now let us shrink ourselves down. Let us leave the grand scale of the towering cumulonimbus and enter the microscopic world inside the cloud. Here, among the billions of tiny droplets and ice crystals, a hidden world of chemistry is at work. This is the world of cloud microphysics, the science of the very small things that happen inside clouds, and it is as beautiful and intricate as anything in nature. A cloud droplet is a tiny sphere of water, typically 10 to 20 micrometers in diameter. It is far too small to see with the naked eye. 1 million of these droplets would fit inside a single raindrop, and yet each one is a miniature chemical laboratory. The surface of the droplet is where the liquid water meets the surrounding air, and at this interface, this thin, invisible boundary between two phases of matter, chemical exchanges are constantly occurring. Gases from the air dissolve into the water. Dissolved substances react with each other within the water. New molecules form. Old molecules break apart. Products escape back into the air. The droplet is alive with chemistry, a tiny, busy world unto itself. Let us watch, slowly, as a cloud droplet forms. It begins with a cloud condensation nucleus, that tiny particle we discussed earlier. Perhaps it is a grain of sea salt, less than a micrometer across, lifted from the ocean's surface by the bursting of a bubble in the surf. Perhaps it is a particle of ammonium sulfate, formed by the reaction of ammonia gas with sulfuric acid vapor high in the atmosphere. Perhaps it is a speck of organic material, a fragment of a terpene molecule that was emitted by a pine tree and oxidized in the atmosphere to form a low volatility product that condensed into a tiny particle. Whatever its origin, this particle is now floating in the air inside the cloud, surrounded by water vapor that has reached the saturation point. Water molecules begin to condense onto the particle's surface. The first few molecules of water attach themselves, forming a thin film. Then more molecules arrive. The film grows into a tiny droplet. The particle is now at the center of the droplet, like a seed at the heart of a fruit, and its chemical nature influences the chemistry of the water around it. If the condensation nucleus is a particle of sea salt sodium chloride, then the sodium and chloride ions dissolve into the surrounding water, making the droplet slightly salty. This dissolved salt has an interesting effect. It lowers the vapor pressure of the water in the droplet, making it easier for additional water molecules to condense onto it. This is the Raoult effect, and it means that soluble particles are more effective condensation nuclei than insoluble ones. The salt particle attracts water, helping the droplet grow more easily. If the condensation nucleus is a sulfate particle, formed from the oxidation of sulfur dioxide in the atmosphere, then the droplet becomes slightly acidic from the moment it forms. Sulfuric acid dissolves completely in water, releasing hydrogen ions, protons, that lower the pH of the droplet. This acidity makes the droplet a more aggressive chemical environment, capable of dissolving metal ions from any mineral particles it encounters and of catalyzing certain oxidation reactions. If the particle is organic, a bit of oxidized terpene or a fragment of combustion soot coated with organic material, then the chemistry of the droplet is more complex. Organic compounds can form surface films on the droplet that alter its interaction with the surrounding air, changing the rate at which gases dissolve into it or evaporate from it. They can also participate in photochemical reactions within the droplet, absorbing sunlight and producing radicals that drive further chemistry. Once the droplet has formed, gases from the surrounding air begin to dissolve into it. This process is governed by a principle called Henry's law, which describes the equilibrium between a gas in the atmosphere and the same gas dissolved in a liquid. Henry's law tells us that the amount of gas that dissolves in a liquid is proportional to the partial pressure of that gas in the surrounding air. Gases that are highly soluble in water, like sulfur dioxide, hydrogen peroxide, and ammonia, dissolve readily and in large quantities. Gases that are less soluble, like oxygen, nitrogen, and methane, dissolve in much smaller amounts. And carbon dioxide, which has moderate solubility, dissolves and then reacts with the water to form carbonic acid, a weak acid that gently lowers the pH of the droplet. The pH of a cloud droplet, the measure of its acidity, is a remarkably important quantity because it determines which chemical reactions can occur within the droplet and how fast they proceed. In a clean atmosphere, far from any source of pollution, the pH of cloud water is typically around 5.6. This slight acidity is entirely due to the dissolved carbon dioxide, which is always present in the atmosphere. But in polluted air, where sulfur dioxide and nitrogen oxides are present in elevated concentrations, the pH of cloud water can drop to 4 or 3, or in extreme cases, even lower. This makes the cloud water as acidic as vinegar or lemon juice. This acidic cloud water is corrosive. It can dissolve metals. It can damage the surfaces of buildings and monuments. And when it falls to the ground as rain, it can harm the ecosystems it touches. One of the most important reactions in cloud chemistry is the oxidation of sulfur dioxide to sulfuric acid. Let us walk through this reaction slowly, because it illustrates beautifully how the microscopic chemistry of a cloud droplet connects to the large-scale environmental issue of acid rain. Sulfur dioxide is emitted into the atmosphere by volcanoes, by the burning of coal and oil, and by certain industrial processes. It is a gas with a sharp, acrid smell, and it is moderately soluble in water. When sulfur dioxide dissolves in a cloud droplet, it reacts with the water to form sulfurous acid, a weak acid containing sulfur in a partially oxidized state. This sulfurous acid sits in the droplet, waiting to be further oxidized. The oxidation agent that most commonly converts sulfurous acid to sulfuric acid inside cloud droplets is hydrogen peroxide, H2O2. Hydrogen peroxide is a trace gas in the atmosphere, produced by photochemical reactions involving the hydroperoxyl radical. It is quite soluble in water, so it dissolves readily into cloud droplets. Once inside the droplet, hydrogen peroxide reacts quickly with the dissolved sulfurous acid, converting it to sulfuric acid, a strong acid that dissociates completely in water, releasing hydrogen ions and sulfate ions. This reaction is fast and efficient, proceeding in a matter of minutes under typical cloud conditions. Ozone is another oxidizing agent that can convert sulfurous acid to sulfuric acid inside cloud droplets, though the reaction with ozone is somewhat slower than the reaction with hydrogen peroxide. And dissolved metal ions, particularly iron and manganese, which may be present in the droplet if the condensation nucleus contained mineral dust, can catalyze the reaction as well, speeding it up under certain conditions. The sulfuric acid produced inside the cloud droplet remains dissolved in the water. It does not evaporate back into the air, because sulfuric acid has an extremely low vapor pressure. So once it is formed, it stays in the droplet, making the water more and more acidic. When the cloud eventually produces rain, this sulfuric acid is carried to the ground in the raindrops, contributing to the phenomenon of acid deposition. But sulfur is not the only element undergoing chemical transformations inside cloud droplets. Nitrogen chemistry is also active. Nitrogen dioxide, one of the nitrogen oxides produced by combustion and by lightning, dissolves in cloud water and undergoes a series of reactions. It can react with water to form nitric acid and nitrous acid simultaneously. It can also react with the hydroxyl radical in the gas phase to form nitric acid, which then dissolves into the cloud water. Nitric acid, like sulfuric acid, is a strong acid, and it contributes to the acidity of rain. Organic chemistry within cloud droplets is even more complex. Volatile organic compounds molecules containing carbon and hydrogen, and often oxygen, emitted by vegetation and by human activities, dissolve into cloud water and undergo oxidation reactions. These reactions can produce organic acids like formic acid and acetic acid, which contribute to the acidity of cloud water. They can also produce larger, less volatile organic molecules that remain in the droplet and contribute to the formation of secondary organic aerosol, tiny particles of organic material that can persist in the atmosphere long after the cloud has evaporated. There is also the fascinating world of heterogeneous reactions, chemical reactions that occur not in the gas phase or in the liquid phase, but at the interface between the two, or on the surfaces of solid particles. The surfaces of aerosol particles within cloud droplets and the surfaces of the droplets themselves provide unique chemical environments where reactions can proceed by different pathways and at different rates than they would in the bulk gas or liquid. For example, the reaction of nitrogen pentoxide with water. In the gas phase, this reaction is extremely slow, essentially negligible. But on the surface of an aerosol particle or a cloud droplet, the reaction proceeds readily, converting nitrogen pentoxide into nitric acid. This heterogeneous pathway is one of the main routes by which reactive nitrogen oxides are converted into nitric acid, a form that is easily removed from the atmosphere by rain. Now let us think about what happens at the colder, higher levels of the cloud where ice crystals are forming. The chemistry of ice is different from the chemistry of liquid water. Gases are generally much less soluble in ice than in liquid water. This means that when a liquid cloud droplet freezes, many of the dissolved gases and ions are expelled from the growing ice lattice. They are concentrated into the remaining liquid, a thin film of highly concentrated solution that coats the surface of the ice crystal or is trapped in tiny pockets within it. These concentrated solutions can be extraordinary chemical environments. The concentration of reactants may be orders of magnitude higher than in the original liquid droplet, and this concentration effect can dramatically accelerate certain chemical reactions. Reactions that would be slow or negligible in the dilute solution of a cloud droplet may proceed rapidly in the concentrated brine at the surface of an ice crystal. This is one of the ways in which the phase transitions inside a cloud, the freezing and melting of water, influence the chemistry of the atmosphere. The expulsion of gases during freezing also returns dissolved species to the air inside the cloud. When a supercooled droplet freezes suddenly, the dissolved gases are released in a burst, temporarily increasing the local concentrations of these gases in the air surrounding the newly formed ice crystal. This degassing can influence the gas phase chemistry in the immediate vicinity of the crystal, creating localized chemical hotspots within the cloud. And then there are the collisions between ice particles. We mentioned earlier that collisions between falling Graupel particles and smaller ice crystals transfer electrical charge, building the charge separation that produces lightning. But these collisions also have chemical consequences. The surfaces of ice particles may carry adsorbed gases and thin films of liquid or quasi-liquid water, and when two particles collide, these surface species can be exchanged, redistributed, or chemically altered by the energy of the impact. The details of these processes are still an active area of research, and they remain one of the frontiers of cloud chemistry. All of this, the droplet formation, the gas dissolution, the sulfur and nitrogen chemistry, the organic reactions, the heterogeneous processes, the ice chemistry, the concentration effects during freezing, all of this is happening simultaneously in billions of droplets and crystals throughout the cloud. It is a staggeringly complex chemical system, and it is one that scientists are still working to fully understand. But from our quiet vantage point, we do not need to understand every reaction. We simply need to appreciate the beauty of it. Inside a cloud that looks, from the outside, like nothing more than a mass of gray moisture, there is a hidden universe of chemistry. Molecules are forming and breaking. Ions are dissolving and recombining. Acids are strengthening and being neutralized. Surfaces are catalyzing reactions that could not happen any other way. And all of it in silence, all of it in darkness, all of it in the invisible, microscopic world of cloud microphysics. Let yourself drift with those droplets for a moment. Imagine yourself floating inside the cloud, carried gently by the updraft, surrounded by a soft, gray mist of water and ice. The air is cool and damp. There is no sound except the faint whisper of air moving past you. No light except the dim, diffused glow filtering through the cloud from the distant sun. Everything is still, everything is calm, and everything is chemistry. And now we come to lightning. Of all the phenomena in a thunderstorm, lightning is the most dramatic, the most visible, the most memorable. A flash of light that lasts less than a second. A sound that rolls across the sky like the deep voice of the atmosphere itself. But in that briefest of moments, in that flicker of brilliance, an extraordinary amount of chemistry occurs. Lightning is, in every sense, a chemical event as much as it is an electrical one. Let us begin with how lightning forms. We spoke a moment ago about the charge separation that occurs when ice particles collide inside the cloud. As millions of these tiny collisions accumulate over time, the cloud develops a distinct electrical structure. The lower part of the cloud, where the heavier Graupel particles accumulate, builds up a region of negative charge. The upper part of the cloud, where the lighter ice crystals are carried upward by the updraft, builds up a region of positive charge. There may also be a small pocket of positive charge near the base of the cloud, created by the interaction of rain and the electrical field. This charge separation creates an enormous electrical field, a difference in voltage between the top and bottom of the cloud that can reach hundreds of millions of volts. The electrical potential energy stored in this field is immense, comparable to the energy stored in a small nuclear device, though distributed across a volume of air many cubic kilometers in extent. The air between these charged regions is normally an excellent insulator. Under ordinary conditions, at the pressures and temperatures found in the troposphere, air does not conduct electricity. The molecules of nitrogen and oxygen are electrically neutral, and they resist the flow of current. But when the electrical field becomes strong enough, when it exceeds a threshold known as the breakdown voltage, the air can no longer resist. Its insulating properties fail, and a cascade begins. A few free electrons, always present in the air from cosmic rays and natural radioactivity, are accelerated by the intense electrical field. They gain enough energy to knock electrons off the air molecules they collide with, creating more free electrons and positively charged ions. These new free electrons are also accelerated by the field, and they too collide with air molecules, freeing still more electrons. This is an avalanche process, and it happens with extraordinary speed. In microseconds, a narrow channel of ionized air, a plasma, extends downward from the base of the cloud in a series of stuttering, branching steps. This is the stepped leader, and it is the first visible part of the lightning process, though it is too faint and too fast for the human eye to see. As the stepped leader approaches the ground, it induces a concentration of positive charge on the surface below. Streamers of positive ions reach upward from tall objects, trees, buildings, lightning rods, exposed hilltops reaching toward the descending leader. When one of these upward streamers connects with the stepped leader, a complete conducting channel is established between the cloud and the ground, and in that instant, the main discharge occurs. The return stroke, the bright flash that we see as lightning, is a massive surge of current flowing upward through the channel established by the leader. The current can reach 30,000 amperes or more, and the energy released heats the air in the channel to approximately 30,000 Kelvin, roughly 5 times the temperature of the visible surface of the sun. This heating is so rapid and so intense that the air in the channel expands explosively, creating a shock wave that we hear as thunder. But it is the chemistry within that superheated channel that interests us most tonight. At 30,000 Kelvin, the air in the lightning channel is no longer air in any ordinary sense. It is a plasma, a mixture of free electrons, positive ions, and neutral atoms and molecules, all in a state of extreme agitation. At these temperatures, the kinetic energy of the particles is far greater than the strength of any chemical bond. Molecular bonds are broken as easily as cobwebs. Nitrogen molecules, with their famously strong triple bonds, are torn apart. Oxygen molecules are dissociated into individual atoms. Water molecules, if present, are shattered into hydrogen and oxygen atoms and hydroxyl radicals. And in the cooling aftermath of the flash in the microseconds and milliseconds after the peak temperature is reached, these freed atoms recombine in new configurations. Nitrogen atoms, suddenly liberated from their molecular partners, combine with the abundant oxygen atoms in the surrounding air to form nitrogen monoxide, NO. This is a simple molecule, one nitrogen atom bonded to one oxygen atom, but its formation is enormously significant. This process is called nitrogen fixation, and it is one of the most important chemical processes on Earth. Nitrogen fixation is the conversion of atmospheric nitrogen gas, which is chemically inert and biologically unavailable, into reactive nitrogen compounds that can be used by living organisms. For billions of years, lightning was one of the primary natural mechanisms of nitrogen fixation on this planet. Long before bacteria evolved the ability to fix nitrogen, and long before humans invented the Haber-Bosch process for industrial nitrogen fixation in the early 20th century, lightning was breaking the stubborn triple bond of nitrogen and creating the reactive nitrogen compounds that life needs to build proteins and DNA. The nitrogen monoxide produced by lightning does not remain as nitrogen monoxide for long. Once it disperses from the cooling lightning channel into the surrounding air, it quickly reacts with additional oxygen molecules, the ordinary O2 in the atmosphere, to form nitrogen dioxide, NO2. This reaction is relatively fast, occurring over a timescale of seconds to minutes, depending on the concentration of ozone present. The ozone pathway is particularly efficient. Nitrogen monoxide reacts with ozone to form nitrogen dioxide and oxygen gas. This conversion is an important step because nitrogen dioxide is the molecule that drives the photochemical production of ozone when it absorbs ultraviolet light. Together, nitrogen monoxide and nitrogen dioxide are referred to as nitrogen oxides, or NOx. These nitrogen oxides are among the most chemically active species in the atmosphere. They are central to the photochemical cycles that produce and destroy ozone. They influence the concentration of the hydroxyl radical, the atmosphere's primary cleaning agent. They contribute to the formation of nitric acid, which is removed from the atmosphere by rain. They participate in the chemistry of aerosol formation. In short, the nitrogen oxides produced by a single lightning flash ripple outward through the atmospheric chemical system, influencing dozens of other reactions and processes. How much nitrogen oxide does a single flash produce? This is a question that scientists have studied intensively, and the answer is still somewhat uncertain. Estimates range from about 2 to 40 kilograms of nitrogen per flash, with most estimates clustering around 4 to 8 kilograms. This may not sound like much, a few kilograms from a single flash, but when you multiply that by the roughly 1.5 billion lightning flashes that occur globally each year, the total production is enormous. Current estimates suggest that lightning produces somewhere between 2 and 8 teragrams of nitrogen per year, that is, 2 to 8 million metric tons. This is a significant fraction of the total natural nitrogen fixation on Earth, comparable to the amount fixed by all the nitrogen-fixing bacteria in all the world's soils and oceans combined. Lightning also produces other chemical species besides nitrogen oxides. The intense heat of the lightning channel causes the dissociation of oxygen molecules into individual oxygen atoms. These oxygen atoms are highly reactive, and many of them immediately combine with nearby oxygen molecules to form ozone. This lightning-produced ozone is a localized effect. It is produced in the immediate vicinity of the lightning channel, but it contributes to the overall ozone budget of the troposphere. The characteristic fresh, sharp smell that people sometimes notice before or after a thunderstorm is often attributed to this ozone, which is carried downward from the storm by descending air currents and diffuses into the air near the surface. The lightning channel also produces various free radicals, hydroxyl radicals, formed by the dissociation of water molecules in the hot channel, oxygen radicals, formed by the dissociation of oxygen, hydroperoxyl radicals, formed by the recombination of hydrogen atoms with oxygen. These radicals are extraordinarily reactive and short-lived. They exist for only fractions of a second before reacting with something, but in their brief existence, they initiate chains of chemical reactions that process and transform the gases in the air surrounding the lightning channel. There is another chemical product of lightning that is worth mentioning, nitrous oxide, N2O, also known as laughing gas. Nitrous oxide is produced in small quantities during the high-temperature reactions between nitrogen and oxygen in the lightning channel. It is a long-lived greenhouse gas and an ozone-depleting substance. While the amount produced by any single lightning flash is tiny, the cumulative effect of all the lightning on Earth contributes modestly to the global budget of this important trace gas. Let us pause for a moment and consider the scale and beauty of what we are describing. A single lightning flash lasting less than a second heats a narrow channel of air to 5 times the temperature of the sun's surface. In that channel, for a few brief milliseconds, chemistry happens that cannot happen anywhere else in the troposphere under natural conditions. Bonds that cannot be broken by any other atmospheric process are shattered by the sheer thermal energy of the discharge. New molecules are born: nitrogen monoxide, ozone, free radicals that did not exist a moment before. And then the channel cools rapidly over the span of a few seconds, and the newly created molecules disperse into the surrounding air, where they begin their own quiet chemical journeys through the atmosphere. It is like a tiny forge, hidden inside the storm, briefly lit, briefly hot, and then dark again. And in that moment of light and heat, atoms are rearranged in ways that influence the chemistry of the entire planet. Globally, there are roughly 40 to 50 lightning flashes per second. That is approximately 4 million flashes per day, about 1.5 billion flashes per year. Each flash is a tiny chemical factory, converting unreactive atmospheric nitrogen into reactive nitrogen oxides, producing ozone, generating radicals, altering the composition of the air. Together, these billions of tiny factories make a substantial contribution to the chemistry of the global atmosphere. So, the next time you see a flash of lightning or hear the distant rumble of thunder rolling across the sky, remember that what you are witnessing is not just a discharge of electricity, it is a chemical event. A moment of creation, a tiny, brilliant spark in which the atmosphere is transformed gently and irrevocably, one molecule at a time. And then it passes. The thunder fades into the distance. The rain continues, soft and steady. And the invisible molecules, newly born in the heart of the flash, begin their quiet, patient work. Let us turn now to one of the most important families of molecules in the atmosphere, the reactive oxygen species. These are molecules and molecular fragments that contain oxygen in highly reactive forms, and they are the workhorses of atmospheric chemistry. They break down pollutants. They regulate the lifetimes of greenhouse gases. They produce and destroy ozone, and thunderstorms influence their concentrations in profound and interconnected ways. We should begin with ozone itself, because ozone is absolutely central to this story. Ozone, O3, is a molecule made of 3 oxygen atoms bonded together in a bent shape. Unlike ordinary oxygen gas, O2, which is a stable and relatively unreactive molecule with 2 atoms, ozone has an extra atom that makes it chemically active and somewhat unstable. It has a distinctive, sharp, fresh smell, the smell of electrical equipment, of photocopiers, of the air near a sparking wire. And it has properties that make it one of the most important molecules in the atmosphere. In the stratosphere, that calm, dry layer above the troposphere, ozone absorbs ultraviolet radiation from the sun. The UVB and UVC wavelengths of sunlight carry enough energy to damage DNA, cause skin cancer, and harm the tissues of plants and animals. The stratospheric ozone layer, sometimes called the ozone shield, absorbs most of this radiation before it reaches the surface, protecting life on Earth. This is the ozone we are grateful for, the ozone that has made the surface of our planet habitable for complex life. But ozone in the troposphere, at the altitudes where we live and where thunderstorms operate, is a different matter. Here, ozone is a pollutant. In high concentrations, it irritates the lungs, aggravates asthma and other respiratory conditions, reduces lung function, and can even cause premature death in vulnerable populations. It damages crops, reducing yields and harming the food supply. It contributes to the formation of smog, and it is a greenhouse gas, absorbing and re-emitting infrared radiation and contributing to the warming of the planet. The concentration of tropospheric ozone is determined by a balance between production and destruction, and this balance is influenced significantly by thunderstorms. The production of tropospheric ozone depends primarily on nitrogen oxides and sunlight. The key reaction is the photolysis of nitrogen dioxide. When nitrogen dioxide, NO2, absorbs a photon of ultraviolet light with a wavelength shorter than about 420 nanometers, it breaks apart into nitrogen monoxide, NO, and a single oxygen atom in an excited state. This lone oxygen atom is extraordinarily reactive. It immediately combines with an oxygen molecule, O2, in the presence of a third body, typically nitrogen or oxygen, which carries away the excess energy of the reaction. The result is ozone, O3. This is the primary pathway for ozone production in the troposphere, and notice that it requires nitrogen dioxide as a starting material. Without nitrogen dioxide, this photochemical reaction cannot proceed, and ozone cannot be produced. This is why the nitrogen oxides produced by lightning are so important for tropospheric ozone. Every molecule of nitrogen monoxide produced by lightning is eventually converted to nitrogen dioxide, and every molecule of nitrogen dioxide in the presence of sunlight can produce a molecule of ozone. But the story is more nuanced than this simple picture suggests. The production of ozone from nitrogen dioxide is part of a cycle, a set of reactions that interconvert nitrogen monoxide and nitrogen dioxide while producing and consuming ozone. In this cycle, ozone is produced when nitrogen dioxide is photolyzed, but ozone is also consumed when it reacts with nitrogen monoxide to reform nitrogen dioxide. If these were the only reactions, there would be no net production of ozone. The cycle would simply spin, producing and consuming ozone in equal amounts. Net ozone production occurs when other reactions intervene to convert nitrogen monoxide back to nitrogen dioxide without consuming ozone. The most important of these reactions involves the hydroperoxyl radical HO2, which reacts with nitrogen monoxide to form nitrogen dioxide and the hydroxyl radical. This reaction recycles nitrogen monoxide to nitrogen dioxide without using up ozone, allowing the photolysis of the resulting nitrogen dioxide to produce an additional molecule of ozone. The volatile organic compounds in the atmosphere, both natural and human-emitted, feed into this cycle by producing hydroperoxyl and organic peroxyl radicals through their own oxidation reactions. Here is where thunderstorms enter the picture most dramatically. Lightning produces nitrogen oxides in the upper troposphere, where the air is relatively clean and the concentration of competing chemical species is low. In this environment, the ozone production efficiency, the amount of ozone produced per molecule of nitrogen oxide, is higher than at the surface, because there are fewer reactions consuming the nitrogen oxides before they can participate in the ozone-producing cycle. Furthermore, the ozone produced in the upper troposphere has a longer chemical lifetime than ozone near the surface, because the concentrations of the species that destroy ozone are lower at high altitude, and the ozone in the upper troposphere is a particularly effective greenhouse gas. Ozone's greenhouse effect depends on the temperature contrast between the emitting layer and the surface. In the cold upper troposphere, ozone absorbs infrared radiation from the warm surface below and re-emits it at the much colder temperature of its surroundings, creating a significant net warming effect. This means that the ozone produced from lightning-generated nitrogen oxides in the upper troposphere has a disproportionately large impact on climate compared to ozone near the surface. Now, let us turn to the hydroxyl radical, because the hydroxyl radical is the other half of this reactive oxygen story, and it is, in many ways, the most important molecule in the troposphere. The hydroxyl radical, OH, is a molecular fragment consisting of a single oxygen atom bonded to a single hydrogen atom. It is extraordinarily reactive. It will react with almost any organic molecule, and many inorganic ones, that it encounters. Its reactions are fast, often occurring at nearly the rate at which the molecules collide, which is the maximum possible speed for a chemical reaction, and its effects are profound. The hydroxyl radical is responsible for the removal of most atmospheric pollutants and greenhouse gases. It breaks down methane, which would otherwise accumulate to dangerous levels. It oxidizes carbon monoxide. It initiates the degradation of volatile organic compounds. It reacts with sulfur dioxide, contributing to the formation of sulfuric acid. It is, without exaggeration, the primary cleaning agent of the atmosphere. The concentration of the hydroxyl radical in the troposphere is tiny, roughly 1 million molecules per cubic centimeter of air, which is less than 1 part per trillion. For comparison, the concentration of nitrogen is about 20 quintillion molecules per cubic centimeter. The hydroxyl radical is a ghost in the atmospheric machine, invisible and nearly undetectable, but absolutely essential. Thunderstorms influence the hydroxyl radical in several interconnected ways. First, they produce nitrogen oxides, which drive the catalytic cycle that regenerates hydroxyl radicals from hydroperoxyl radicals. Second, they transport water vapor to high altitudes, where the photolysis of ozone and subsequent reaction with water vapor produces hydroxyl radicals. Third, they directly produce hydroxyl radicals in the lightning channel through the thermal dissociation of water vapor. And fourth, they redistribute the chemical precursors of the hydroxyl radical ozone, water vapor, and nitrogen oxides throughout the troposphere, influencing where and when hydroxyl radicals are produced. There is a beautiful symmetry to all of this. Lightning produces nitrogen oxides. Nitrogen oxides drive the production of ozone. The photolysis of ozone produces excited oxygen atoms. Excited oxygen atoms react with water vapor to produce hydroxyl radicals. Hydroxyl radicals react with pollutants and greenhouse gases, cleaning the atmosphere. And the products of those reactions, the hydroperoxyl radical and other species, are recycled back through the system by the very nitrogen oxides that started the process. It is a cycle, an elegant chemical wheel, driven in part by the energy of thunderstorms, continuously turning, continuously cleaning the air. And all of it happens invisibly, in the air around us, in the air you are breathing right now, The reactive oxygen chemistry of the atmosphere is a vast, quiet machine, and thunderstorms are one of its most powerful engines. Close your eyes, if they are not already closed. Imagine the atmosphere as a quiet ocean of molecules, slowly drifting, slowly reacting, slowly cleaning itself. Somewhere, high above, a flash of lightning creates a tiny burst of new molecules. Those molecules drift outward, reacting as they go, setting off chains of chemistry that ripple through the air like gentle waves. And somewhere else, a hydroxyl radical, born from the marriage of light and water, reaches out and gently dismantles a molecule of methane, breaking it into pieces that will eventually become carbon dioxide and water, quietly, gently, one molecule at a time. The atmosphere takes care of itself. It has been doing so for billions of years, and thunderstorms help it along, providing the energy and the raw materials that keep the chemical cycles turning. Rest now for a moment. Let the chemistry drift around you, invisible and gentle. There is more to explore, but there is no hurry. The molecules are patient, and so can we be. Let us follow a single molecule of nitrogen monoxide as it leaves the lightning channel and begins its journey through the atmosphere. This is a molecule that did not exist a few seconds ago. It was created in the briefest flash of heat, born from the violent separation of a nitrogen molecule and the immediate union of one of its atoms with an oxygen atom. And now it is free, drifting in the air, carrying with it the energy and the intent, if we may use such a word, of the lightning that created it. In the first few seconds after the flash, the nitrogen monoxide molecule is surrounded by other molecules that were also created by the lightning. Other nitrogen monoxide molecules, some ozone, some free radicals. The air in the immediate vicinity of the lightning channel is chemically altered. A narrow tube of transformed atmosphere extending from the cloud to the ground, or from one part of the cloud to another. This tube of altered air is sometimes called the lightning channel residual, and it contains elevated concentrations of nitrogen oxides, ozone, and radicals. Within seconds, this tube begins to disperse. The turbulence inside the cloud mixes the lightning-produced molecules with the surrounding air, diluting their concentrations. The nitrogen monoxide molecules spread outward, each one drifting on its own path, carried by the eddies and currents of the storm. Our nitrogen monoxide molecule drifts upward, carried by the updraft toward the top of the cloud. Along the way, it encounters a molecule of ozone. The two molecules react. The nitrogen monoxide takes one of the ozone's 3 oxygen atoms, converting the ozone to ordinary oxygen gas and converting itself to nitrogen dioxide. This reaction happens quickly, in a fraction of a second, and now our molecule has changed its identity. It is no longer nitrogen monoxide. It is nitrogen dioxide, a molecule of 1 nitrogen atom and 2 oxygen atoms. The nitrogen dioxide molecule continues to drift upward. It is expelled from the top of the storm in the anvil outflow, carried eastward by the high-altitude winds. It travels 50 kilometers, 100 kilometers, 200 kilometers from the storm that created it. Along the way, it drifts through air that is clean and cold and bathed in ultraviolet light. When the sun rises the next morning, a photon of ultraviolet light strikes our nitrogen dioxide molecule. The photon has just the right amount of energy to break the bond between the nitrogen atom and one of the oxygen atoms. The molecule shatters. A molecule of nitrogen monoxide is released, along with a single, highly reactive oxygen atom. This oxygen atom immediately reacts with an oxygen molecule to form ozone. A new molecule of ozone has been created, far from the storm, far from the lightning, by the photolysis of a nitrogen dioxide molecule that was itself born from lightning-produced nitrogen monoxide. And so the chemistry continues. The nitrogen monoxide that was released goes on to react with another ozone molecule, reforming nitrogen dioxide. The nitrogen dioxide absorbs another photon, produces another oxygen atom, creates another ozone molecule. The cycle repeats over and over, producing ozone with each turn of the wheel. This is the photochemical ozone production cycle, and it is powered, in this case, by a nitrogen oxide molecule that was born in a lightning flash in a thunderstorm hundreds of kilometers away and many hours ago. Eventually, after hours or days, the nitrogen dioxide molecule encounters a hydroxyl radical. The two react, forming nitric acid, HNO3. Nitric acid is a stable molecule, and it does not easily participate in further gas phase chemistry. It is sticky, it adheres to surfaces, and dissolves readily in water. Eventually, it is washed out of the atmosphere by rain, or it deposits onto a leaf or a soil surface. The nitrogen atom that was once part of an inert nitrogen molecule in the atmosphere, that was liberated by lightning, that became nitrogen monoxide, then nitrogen dioxide, then participated in the production of ozone, has now become part of nitric acid and has been removed from the atmosphere entirely. On the ground, in the soil, that nitric acid is taken up by plant roots. The nitrogen is incorporated into an amino acid, then into a protein, then into the body of the plant. Perhaps the plant is eaten by an animal. The nitrogen passes through the food web, cycling through organisms, until eventually it is returned to the soil by decomposition. There, denitrifying bacteria convert it back to nitrogen gas, which escapes into the atmosphere, closing the cycle. The journey of a single nitrogen atom, from atmospheric gas to lightning product, to atmospheric oxidant, to rainwater nutrient, to living tissue, and back again, may take days, or months, or years. It is a journey that has been repeated countless times, by countless atoms, across billions of years of Earth history, and it all begins, and is continually renewed, by the chemistry of thunderstorms. And now the rain begins to fall. After all the chemistry we have explored inside the cloud, the formation of droplets, the dissolution of gases, the oxidation of sulfur and nitrogen, the ice crystal chemistry, the charge separation, the lightning, the storm releases its water back to the earth. Rain falls, and as it falls, softly, steadily, it carries with it the chemical memory of everything the cloud has experienced. A raindrop does not form in an instant. It grows, slowly and patiently, from the tiny cloud droplets we described earlier. Those droplets, just 10 or 20 micrometers across, are far too small to fall as rain. They are too light to overcome the gentle updrafts inside the cloud and the resistance of the air around them. To become rain, they must grow much larger, and this growth takes time. In warm clouds, where there is no ice, droplets grow by collision and coalescence. Larger droplets, which fall slightly faster than smaller ones due to gravity, sweep up smaller droplets in their path, merging with them and growing larger. As they grow, they fall faster, sweeping up even more droplets, growing faster still. This is a cascade process, a snowball rolling downhill, and it can take a droplet from 10 micrometers to 2 millimeters, from the size of a cell to the size of a small bead in perhaps 20 to 30 minutes. In cold clouds, where ice crystals coexist with supercooled water droplets, the Bergeron process drives growth more efficiently. The ice crystals grow at the expense of the liquid droplets, pulling water vapor from the air around them and converting it directly into ice. The crystals grow into snowflakes, intricate, hexagonal structures of branching ice that are large enough to fall. As they fall through the cloud, they may collide with other crystals and aggregate into larger snowflakes. And when they fall below the freezing level, the altitude at which the temperature rises above 0 degrees Celsius, they melt into raindrops. A typical raindrop arriving at the ground is roughly 1 to 3 millimeters in diameter. It contains about 1 million times more water than a cloud droplet. It has been falling for several minutes, traveling from the cloud base perhaps 2 or 3 kilometers above the ground through layers of air that may be clean or polluted, warm or cool, humid or dry. And throughout that journey, the raindrop has been undergoing chemical changes. Inside the raindrop is a solution, a cocktail of dissolved gases, ions, and molecules that reflects the chemical history of the cloud in which the drop was born. There is dissolved carbon dioxide, forming carbonic acid. There may be sulfuric acid, formed from the oxidation of dissolved sulfur dioxide. There may be nitric acid, formed from the dissolution of nitrogen dioxide or from the scavenging of gas-phase nitric acid. There may be ammonium ions from the dissolution of ammonia. There are the ions from the original condensation nucleus, perhaps sodium and chloride from sea salt, or sulfate from an ammonium sulfate particle, or a complex mixture of organic compounds from a biogenic aerosol. As the raindrop falls from the cloud toward the ground, it passes through air that may contain different gases and particles than the air inside the cloud, and additional chemistry occurs during this descent. This process is called below-cloud scavenging, and it is one of the most important mechanisms by which rain cleans the atmosphere. As the raindrop falls through air containing gases like sulfur dioxide, nitrogen dioxide, or ammonia, these gases dissolve into the drop according to Henry's law. The drop acts like a tiny sponge, absorbing gases from the air as it passes through. The efficiency of this scavenging depends on the solubility of the gas, the size of the raindrop, and the concentration of the gas in the surrounding air. Highly soluble gases like ammonia and sulfur dioxide are scavenged very efficiently. Less soluble gases like carbon monoxide and methane are scavenged very little. The raindrop also scavenges particles from the air. As it falls, it collides with aerosol particles, dust, pollen, soot, sulfate, sea salt, and captures them, incorporating them into the drop. This process removes particles from the air, transferring them from the atmosphere to the surface. After a rainstorm, the air is often noticeably clearer, and colors seem more vivid, because the rain has removed the fine particles that scatter light and reduce visibility. This scavenging of gases and particles by rain is one of the primary mechanisms of atmospheric cleansing. It is the reason the air smells so fresh after a storm. The rain has literally washed the sky, scrubbing away the pollutants and particles that had accumulated in the lower atmosphere. The pungent freshness of post-storm air, sometimes described as the smell of rain, or by the lovely word petrichor, is the combined effect of ozone carried down from the storm, organic compounds released from the soil by the rain, and the simple absence of the dust and pollutants that normally fill the air. The chemistry of rainwater varies enormously depending on location. In remote regions of the Pacific Ocean, far from any source of pollution, rainwater is nearly pure, just slightly acidic from dissolved carbon dioxide, with a pH of about 5.6. This is the baseline, the natural chemistry of rain in an unpolluted atmosphere. In the industrial regions of the eastern United States, Europe, and East Asia, the pH of rain has historically been much lower, around 4.2 to 4.4, due to the dissolution of sulfuric and nitric acids formed from industrial emissions of sulfur dioxide and nitrogen oxides. This is acid rain, one of the most well-known environmental problems of the 20th century. The effects of acid rain on natural ecosystems have been profound. In the lakes and streams of the Adirondack Mountains, Scandinavia, and other regions downwind of industrial pollution, acidification has harmed fish populations and altered aquatic ecosystems. In forests, acid rain has leached essential nutrients like calcium and magnesium from the soil, weakening trees and making them more susceptible to disease and frost damage. On buildings and monuments, particularly those made of limestone and marble, acid rain has accelerated weathering, dissolving the stone and eroding centuries-old structures. The recognition of these effects in the 1970s and 80s led to significant environmental regulations in many countries. The Clean Air Act in the United States and similar legislation in Europe mandated reductions in emissions of sulfur dioxide and nitrogen oxides from power plants and factories. These regulations have been remarkably successful. Sulfur dioxide emissions in the United States have declined by more than 90% since their peak, and the acidity of rain in the northeastern United States has decreased significantly. Lakes and streams that were once too acidic to support fish are slowly recovering. It is one of the great success stories of environmental policy. But rain is not only a carrier of pollution, it is also a carrier of nutrients. The nitrogen compounds dissolved in rainwater derived from both lightning-produced and human-emitted nitrogen oxides, as well as from ammonia, provide a source of biologically available nitrogen to ecosystems. When rain falls on forests, fields, and oceans, it delivers this nitrogen directly to plants and microorganisms, fertilizing the earth. In remote regions far from human activity, lightning-produced nitrogen in rain is one of the primary sources of new nitrogen entering the ecosystem. Rain also carries other nutrients. Trace elements like iron, manganese, zinc, and copper, dissolved from aerosol particles within the cloud or scavenged from the air below, are delivered to the surface by rain. In the open ocean, where nutrients are scarce, the deposition of iron from dust-bearing rain can stimulate the growth of phytoplankton, tiny marine plants that form the base of the ocean food web and play a crucial role in the global carbon cycle. And rain plays a fundamental role in the long-term carbon cycle. The carbonic acid in rainwater, formed from dissolved carbon dioxide, slowly dissolves carbonate rocks like limestone and dolomite in a process called chemical weathering. This process consumes carbon dioxide from the atmosphere and converts it into dissolved bicarbonate ions, which are carried by rivers to the ocean. In the ocean, these bicarbonate ions are used by marine organisms to build shells and skeletons of calcium carbonate. When these organisms die, their shells sink to the seafloor and are eventually incorporated into sedimentary rocks. Over millions of years, these rocks are subducted into the Earth's interior at tectonic plate boundaries, where the carbon is eventually released back into the atmosphere by volcanic eruptions. This weathering burial volcanism cycle is the longest-term carbon cycle on Earth, operating over timescales of millions to hundreds of millions of years. And it is driven, in part, by rain. Every raindrop that falls on a limestone hillside carries away a tiny amount of dissolved rock, a tiny amount of carbon that will eventually make its way to the ocean and to the deep earth. It is a patient process, imperceptibly slow, but over geological time, it has regulated the concentration of carbon dioxide in the atmosphere and modulated the temperature of the planet. And so the humble raindrop, falling quietly from a storm cloud, is a small but significant player in the chemistry of the planet. It cleans the air, scrubbing away pollutants and particles. It nourishes the soil, delivering nitrogen and trace elements to ecosystems. It weathers the rocks, slowly dissolving the Earth's surface and cycling carbon through the geosphere. It carries the chemical imprint of the storm from the sky to the ground, connecting the chemistry of the atmosphere to the chemistry of the surface in an endless, gentle cycle. Listen to the rain for a moment. Each drop carries a tiny chemical story, a story of dissolved gases and mineral ions, of acids and nutrients, of the atmosphere's chemistry made liquid and brought to Earth. It is a story that has been told countless times before, on every continent, in every ocean, for as long as rain has fallen on this planet. And each time, the chemistry is slightly different, reflecting the unique conditions of that particular storm, that particular place, that particular moment in the life of the atmosphere. Rest now as the rain falls. Let its steady, soft rhythm wash over you. Let the sound carry you deeper into relaxation, deeper into calm. The rain knows what it is doing. It has been cleaning the sky and nourishing the earth for billions of years, and tonight it is helping you rest. We have been exploring the chemistry of thunderstorms from the inside, watching molecules form and react in the intimate, microscopic spaces of cloud droplets and lightning channels. Now let us step back a little and think about how all of this chemistry affects the world we live in, specifically the air we breathe. Thunderstorms have a profound influence on air quality, and they exert that influence through several interconnected mechanisms that are worth exploring slowly and carefully. The first mechanism is the vertical transport we discussed earlier. Thunderstorms act as giant atmospheric pumps, drawing air from near the surface and pushing it into the upper troposphere. This has important consequences for air quality at both ends of the journey. Near the surface, the removal of polluted air by the storm's updraft can temporarily improve air quality. The stale, polluted air that accumulates in the boundary layer on hot, stagnant days is swept up and replaced by cleaner air from the surrounding environment. People sometimes notice this effect on summer afternoons. The air feels fresher, more breathable, in the wake of a thunderstorm. But the pollutants that are lifted do not disappear. They are deposited in the upper troposphere, where they encounter a different chemical environment. Nitrogen oxides that were harmlessly trapped near the surface may now participate in ozone-producing chemistry at high altitude. Volatile organic compounds may be oxidized to form secondary aerosols that persist in the upper atmosphere. The thunderstorm has not removed the pollution, it has redistributed it, moving it from a place where it directly affects human health to a place where it affects atmospheric chemistry and climate on a broader scale. The second mechanism is the production of nitrogen oxides by lightning. We have discussed this chemistry in detail, but its air quality implications deserve further reflection. Nitrogen oxides are precursors to tropospheric ozone, that ground-level pollutant that irritates lungs, aggravates respiratory conditions, and damages vegetation. In the hours and days following a thunderstorm, particularly in warm, sunny conditions when photochemistry is active, the nitrogen oxides produced by lightning can contribute to elevated ozone concentrations near the surface. This is particularly true when downdrafts from the storm carry lightning-produced nitrogen oxides from the upper cloud down toward the ground, or when the storm's outflow spreads nitrogen oxide-enriched air across the surface. This is one of the paradoxes of thunderstorm chemistry. The storm cleans the air in some ways by washing away particles and gases with rain, but it can also degrade air quality in other ways by producing the chemical precursors of ozone pollution. The net effect depends on a delicate balance of factors: the amount of lightning, the pre-existing pollution levels, the amount of rainfall, the intensity of sunlight after the storm, and the wind patterns that distribute the storm's chemical products. The third mechanism is the cleansing effect of rain itself. We described in the previous section how rain scavenges gases and particles from the atmosphere. This wet deposition is one of the most effective means of removing pollutants from the air. A heavy thunderstorm can dramatically reduce the concentration of particulate matter, dust, soot, sulfate, and other fine particles in the air near the surface. After the storm passes, visibility improves. The sky appears deeper and bluer, and the air feels cleaner. This is not just perception, it is real. The rain has physically removed the particles that were scattering light and reducing air quality. There is also the phenomenon of storm outflow. When a thunderstorm produces strong downdrafts, columns of dense, rain-cooled air cascading downward from the middle levels of the cloud, this dense air hits the ground and rushes outward in all directions, like water spilling from an overturned bucket. This outflow, sometimes called a gust front, can push the polluted surface air ahead of it, temporarily worsening air quality in areas downwind. But in the wake of the outflow, the air is typically much cleaner, having descended from higher altitudes where pollution levels are lower and having been washed by rain during its descent. The interaction between thunderstorms and air quality is particularly complex in urban areas, where pollutant concentrations are high and the chemical environment is already loaded with nitrogen oxides and volatile organic compounds. Urban thunderstorms interact with this polluted air in intricate ways. The storm's updraft lofts urban pollutants to high altitude. The rain scrubs some pollutants from the air. The lightning produces additional nitrogen oxides. And the aftermath, the sunny period following the storm, when the washed air is mixed with residual pollutants, can produce a secondary pulse of ozone as the photochemistry recovers. In rural and forested areas, the interaction takes a different form. Forests emit enormous quantities of volatile organic compounds, isoprene, monoterpenes, sesquiterpenes, as a natural byproduct of their metabolism. These biogenic emissions react with the nitrogen oxides produced by lightning to form ozone and secondary organic aerosol. The aerosol can form a visible haze, the famous blue haze of forested mountains that reduces visibility and affects the radiative balance of the atmosphere. Thunderstorms intensify this chemistry by providing fresh nitrogen oxides and by mixing the forest emissions with air from above the canopy. Over the oceans, far from human activity, thunderstorms are essentially the sole significant source of nitrogen oxides. The marine atmosphere is otherwise very clean, with nitrogen oxide concentrations near zero. Lightning provides the nitrogen oxides that drive the photochemical production of ozone over the oceans, and this ozone, in turn, provides the excited oxygen atoms that react with water vapor to produce hydroxyl radicals. Without lightning, the remote marine atmosphere would have much lower concentrations of hydroxyl radicals, which would mean slower removal of methane and other greenhouse gases, which would mean a different climate. The connection between a lightning flash over the Pacific Ocean and the global concentration of methane is not obvious, but it is real and scientifically well established. All of this complexity, the transport, the production, the scavenging, the outflows, the interactions with urban and rural and marine environments happens with every thunderstorm, everywhere on the planet, every day. It is a continuous, global, chemical process, as regular and as essential as the turning of the seasons. And right now, somewhere on Earth, perhaps over the warm waters of the tropics, or over the steaming forests of Central Africa, or over the sun-baked plains of the American Midwest, a thunderstorm is at work. Its updrafts are lifting air from the surface. Its lightning is fixing nitrogen. Its rain is washing the sky. And the air, the invisible ocean of gas that we all share, is being slowly, quietly transformed. Think about that for a moment. The air you breathe tonight has been shaped by thunderstorms. Not just the one you might have seen last week, but by millions of storms over decades and centuries, each one contributing its small chemical signature to the atmosphere. The air is not inert. It is not static. It is a living, breathing, reacting system, constantly being cleaned and renewed and replenished by the storms that sweep across the planet. And right now, the air around you is clean and quiet. The storm has done its work. The chemistry has played out, and you can breathe easily, knowing that the atmosphere is taking care of itself, as it always has. Let us also consider what the storm looks like from below, from the perspective of someone standing in a field as the rain falls around them. The raindrops are not all the same size. Small drops, less than a millimeter in diameter, are nearly spherical, held in shape by surface tension. They fall slowly, swaying in the air like tiny parachutes. Larger drops, 2 or 3 millimeters across, are flattened on the bottom by the resistance of the air as they fall. They look less like spheres and more like tiny hamburger buns, flat on the bottom and rounded on top. The very largest drops, 4 or 5 millimeters, are so distorted by the air that they become unstable. They oscillate and wobble as they fall, and eventually they break apart into smaller drops, which continue their descent independently. Each of these drops, whatever its size, is carrying a unique chemical mixture. The small drops, which have been drifting in the cloud for a longer time, may have accumulated more dissolved gases and a higher concentration of sulfuric or nitric acid. The large drops, which formed more recently by the coalescence of smaller drops, may be more dilute. Drops that fell through a layer of polluted air near the surface may have scavenged different gases than drops that fell through cleaner air. If you could taste the rain, and in fact many of us have, you would taste nothing, or perhaps a faint mineral quality, depending on the chemistry. In very polluted areas, acid rain can have a slightly sour taste, though the acidity is usually too mild to detect. In coastal areas, rain may carry a hint of salt from the sea spray that provided the condensation nuclei. In forested areas, rain sometimes has a faint organic quality from the dissolved terpenes and other compounds emitted by the trees. But the real chemistry of the rain is invisible and tasteless. It is happening at the molecular level, in the thin film of water that coats each drop, in the dissolved gases and ions that permeate the liquid. It is chemistry that you cannot see, cannot taste, cannot smell except, perhaps, for that wonderful, earthy, clean scent that rises from the ground when the rain first touches dry soil, the scent of petrichor. Petrichor. It is one of the loveliest words in the English language, and it describes one of the loveliest scents. The word was coined in 1964 by two Australian mineralogists, and it comes from the Greek words petra, meaning stone, and ichor, meaning the fluid that flows in the veins of the gods in Greek mythology. Petrichor is the scent of rain on dry earth, a warm, earthy, slightly sweet fragrance that rises from the soil when the first drops of rain arrive after a dry spell. The scent has two main chemical components. The first is geosmin, a molecule produced by soil bacteria, particularly the Streptomyces bacteria that are abundant in healthy soils. Geosmin has a distinctive earthy smell, and it is extraordinarily potent. The human nose can detect it at concentrations of just a few parts per trillion. When rain strikes dry soil, the impact of the drops disturbs the soil surface and releases geosmin molecules into the air, where they are carried upward and spread by the wind. The second component is a mixture of volatile organic compounds, oils, and esters that are produced by plants during dry periods and accumulate on the surfaces of rocks and soil. When rain falls, these compounds are washed from the surfaces and released into the air, contributing to the complex, layered fragrance of petrichor. So the scent of rain is, in a very real sense, a chemical message from the soil and the biosphere, triggered by the arrival of the storm's water. It is a bridge between the chemistry of the atmosphere and the chemistry of the living earth, mediated by the simplest of actions, a raindrop striking the ground, and the rain continues to fall, softly, steadily, carrying its invisible cargo of dissolved gases and nutrients from the sky to the earth, cleaning the air, nourishing the soil, linking the atmosphere to the biosphere in an endless, gentle, chemical embrace. The storm is fading now. The lightning has stopped. The thunder has rolled away to some distant horizon and fallen silent. The rain has slowed from a steady downpour to a gentle drizzle, and even the drizzle is easing, thinning, becoming intermittent, a few drops here, a few drops there, falling with soft, irregular taps on the leaves and the ground. The clouds are thinning, breaking apart, separating into fragments that drift across the sky like ships loosening from their moorings. Slivers of dark sky peek through between the clouds, and if you look carefully, you might see a star or two, faint and patient, waiting for the clouds to pass. The dramatic part of the storm is over. The convection has exhausted itself. The updrafts have weakened and died. The electrical field has been discharged. The rain has fallen. The cloud is dissipating, returning its moisture to the atmosphere as the last droplets and crystals evaporate back into the cooling air. But the chemistry continues. In the quiet hours after a storm, when darkness has settled over the landscape and the air is cool and still, a different kind of atmospheric chemistry takes over. This is the nighttime chemistry of the atmosphere, and it is as important in its own quiet, unassuming way as the sunlight-driven chemistry of the daytime. During the day, atmospheric chemistry is dominated by photolysis reactions driven by sunlight. Ultraviolet radiation from the sun provides the energy that breaks apart ozone, nitrogen dioxide, and other molecules, producing the reactive fragments that drive the daytime chemical cycles. The hydroxyl radical, the atmosphere's primary daytime oxidant, is produced by these photolysis reactions and exists in measurable concentrations throughout the sunlit atmosphere. But when the sun sets, the photolysis reactions stop abruptly. The hydroxyl radical, which has a chemical lifetime of only about 1 second, disappears almost immediately. Within a minute or two of sunset, the hydroxyl radical concentration drops to essentially zero. The daytime chemical engine shuts down. But the atmosphere does not sleep. Instead, a different chemical regime takes over, one that operates in the dark, without the energy of sunlight, relying on different oxidants and different reaction pathways. The dominant oxidant of the nighttime troposphere is the nitrate radical NO3, a molecule made of 1 nitrogen atom and 3 oxygen atoms. The nitrate radical is produced by the reaction of nitrogen dioxide with ozone, a reaction that occurs continuously, both day and night. During the day, the nitrate radical is immediately destroyed by sunlight. It absorbs visible light very efficiently and is broken apart into nitrogen dioxide and an oxygen atom within seconds of being formed. So during the day, the nitrate radical exists only as a fleeting, unimportant intermediate. But at night, without sunlight to destroy it, the nitrate radical accumulates. It builds up in the dark air, reaching concentrations of tens to hundreds of parts per trillion, and becomes the dominant oxidizing agent. The nitrate radical is not as reactive as the hydroxyl radical. It is more selective in its targets, preferring to attack molecules with carbon-carbon double bonds, the unsaturated hydrocarbons that are emitted by vegetation and by various human activities. When the nitrate radical reacts with these compounds, it produces a variety of oxidized products, including organic nitrates and nitrogen-containing organic aerosol. These products are generally less volatile than their parent compounds, so they tend to condense onto existing particles or to form new particles, contributing to the haze that often develops on calm nights. In the aftermath of a thunderstorm, the concentrations of nitrogen oxides in the atmosphere are elevated. The lightning has produced a pulse of reactive nitrogen, nitrogen monoxide, and nitrogen dioxide that is now working its way through the chemical system. During the night following the storm, this elevated nitrogen dioxide reacts with ozone to produce the nitrate radical in larger than usual quantities. The nitrate radical then goes on to oxidize organic compounds, producing nitric acid and organic nitrates. The nitrate radical also reacts with nitrogen dioxide to form a molecule called dinitrogen pentoxide, N2O5. This molecule is relatively stable in the gas phase at nighttime temperatures, and it serves as a temporary reservoir of reactive nitrogen. But when dinitrogen pentoxide encounters a surface, whether the surface of an aerosol particle, a cloud droplet, a leaf, or the ground, it reacts rapidly with water to produce 2 molecules of nitric acid. This heterogeneous reaction is an important pathway for removing reactive nitrogen from the atmosphere and converting it into a form nitric acid that can be deposited on the surface by rain or by dry deposition. After a thunderstorm, this nighttime processing of nitrogen oxides is particularly active. The storm has produced a large amount of nitrogen dioxide through its lightning. The ozone produced by the storm provides the oxidant needed to form the nitrate radical, and the elevated humidity after the storm provides the water needed for the heterogeneous reactions that convert dinitrogen pentoxide to nitric acid. The net effect is that much of the nitrogen oxide produced by the storm is converted to nitric acid within hours of the storm's passage, and this nitric acid is then removed from the atmosphere by the next rainfall or by deposition onto surfaces. The cooling of the air after a storm also affects chemistry in subtle ways. As the temperature drops, the rates of many chemical reactions change. Some reactions speed up at lower temperatures, while others slow down. The equilibrium positions of reversible reactions shift. Gases that were in the gas phase during the warm afternoon may condense onto surfaces or into new particles as the air cools. Volatile organic compounds that were fully gaseous during the day may partition into the particle phase at night, changing the chemical composition of the aerosol. Dew formation is another post-storm chemical process. As the surface cools by radiating heat to the sky, the air immediately above the surface cools as well. If it cools to the dew point, water begins to condense on surfaces, on leaves, on grass, on the hoods of cars, on the cool glass of windows. This dew is not pure water. It contains dissolved gases and particles from the air, and it serves as a thin film of reactive solution in which chemistry continues. Ozone, nitrogen dioxide, and sulfur dioxide dissolve into the dew and react, producing acids and other oxidized products. These products are deposited directly on the surfaces beneath the dew, on the cuticles of leaves, on the surfaces of soil particles, on painted and metal surfaces where they can cause damage over time. The thunderstorm's chemistry continues through the night in the upper atmosphere, far above the ground. The storm's updrafts slowly process the nitrogen oxides they injected into the upper troposphere. They react with ozone to form the nitrate radical. The nitrate radical reacts with nitrogen dioxide to form dinitrogen pentoxide. Dinitrogen pentoxide reacts on the surfaces of ice crystals and sulfate aerosol particles to form nitric acid. This processing occurs over hours and days, and it gradually erases the chemical fingerprint of the storm from the upper atmosphere. The storm's chemistry also slowly consumes the ozone that it produced. In the upper troposphere at night, ozone reacts with nitrogen monoxide and with hydroperoxyl radicals, slowly decreasing in concentration. The lifetime of ozone in the upper troposphere is on the order of weeks, so the ozone pulse produced by a single storm persists for some time before being fully processed. But eventually, it too fades, absorbed back into the background chemistry of the atmosphere. There is something deeply peaceful about the nighttime chemistry of the atmosphere. It is slower, quieter, and less dramatic than the daytime photochemistry. The reactions proceed in the dark, without the energetic push of sunlight, relying on the slow, steady encounters between molecules that happen to locate each other in the vastness of the air. There is no urgency. There is no rush. Just the quiet, patient work of molecules in the dark, tidying up after the storm, processing the remnants of the day's chemistry, preparing the atmosphere for tomorrow. And as the night deepens, the atmosphere settles further. The turbulence dies down. The air becomes layered and calm, with the coldest, densest air near the ground and warmer air above a stable configuration known as a temperature inversion. This inversion traps the nighttime chemical products near the surface, preventing them from mixing upward. The air near the ground may become slightly hazy as the organic aerosol produced by the nighttime chemistry accumulates. But high above, the sky is clearing. The last wisps of the storm cloud are dissolving. The stars are coming out, one by one, then in clusters, then in great sweeping rivers of light. The atmosphere above is clear and transparent, its molecules quietly doing their work in the dark. And somewhere, perhaps far away, perhaps on another continent entirely, another storm is beginning to form. A patch of warm ocean is heating the air above it. Water vapor is rising. An updraft is developing. A cloud is growing. The cycle is beginning again, as it always does, as it has done for as long as the earth has had air and water and sunlight. But here, where we are, the night is quiet. The rain has stopped. The clouds have cleared, and the air, refreshed and renewed by the storm's extraordinary chemistry, is clean and cool and still. A good night for rest, a good night for sleep, Now let us zoom out. Let us rise above the single storm, above the single cloud, above the single flash of lightning, and look at the earth as a whole. From this altitude, from this contemplative distance, we can see thunderstorms not as individual events, but as components of a planetary chemical engine, a vast, interconnected system that has been shaping the atmosphere and sustaining the conditions for life for billions of years. At any given moment, there are roughly 1,800 thunderstorms occurring simultaneously around the world. If you could watch the Earth from space, a time-lapse view of the planet turning beneath you, you would see a constant scattering of storms across the tropics and the middle latitudes, flickering like tiny lights on the surface. Most of them are concentrated in the tropics, where the sun's energy is strongest and the air is warmest and most humid. The great thunderstorm factories of the Earth are the tropical landmasses, the Amazon basin, the Congo basin, the maritime continent of Southeast Asia, where warm, moist air and intense solar heating produce thunderstorms almost every afternoon, day after day, year after year. But thunderstorms also occur at higher latitudes, over the Great Plains of North America, over the Mediterranean, over the monsoon regions of South and East Asia. They occur over the oceans, triggered by tropical disturbances and by the interaction of warm ocean currents with cooler air. They even occur in the Arctic, rarely, during the brief summer, when unusual warmth and moisture create the conditions for polar thunderstorms. Together, all these storms produce roughly 40 to 50 lightning flashes per second, a ceaseless global drumbeat of electrical and chemical activity that never pauses, never stops. Roughly 4 million flashes per day, about 1.4 billion flashes per year. Each one a tiny chemical factory, converting inert atmospheric nitrogen into reactive nitrogen oxides, producing ozone, generating hydroxyl radicals, stirring the atmosphere, and redistributing chemicals between the surface and the upper troposphere. The nitrogen oxides produced by all this lightning are a significant input to the global nitrogen cycle. The nitrogen cycle is the set of processes by which nitrogen, the most abundant element in the atmosphere, moves between the air, the biosphere, the oceans, and the soil. Atmospheric nitrogen gas, with its strong triple bond, is biologically unavailable. Living organisms cannot use it directly. It must first be fixed, converted into reactive forms like ammonia, nitrate, or organic nitrogen compounds before it can be incorporated into the molecules of life. The three major pathways of nitrogen fixation on Earth today are biological nitrogen fixation, primarily by bacteria associated with the roots of leguminous plants, and by free-living soil bacteria. Industrial nitrogen fixation through the Haber-Bosch process, which converts atmospheric nitrogen to ammonia using high temperatures and pressures, and lightning nitrogen fixation, which converts atmospheric nitrogen to nitrogen oxides through the extreme temperatures of the electrical discharge. Lightning contributes an estimated 2 to 8 teragrams of nitrogen per year to the global nitrogen budget. This is a modest fraction of the total fixation. Biological fixation contributes perhaps 100 to 300 teragrams per year, and industrial fixation contributes about 150 teragrams per year. But lightning fixation has unique importance because it occurs in the upper troposphere, where its chemical products have different fates and different effects than nitrogen fixed at the surface. And before the advent of industrial nitrogen fixation in the early 20th century, and before the spread of intensive agriculture, lightning's contribution was proportionally much larger. In the deep past, billions of years ago, when the Earth was young and life was just beginning, lightning may have been the dominant source of fixed nitrogen on the planet. In an atmosphere that lacked free oxygen, and in a biosphere that had not yet evolved the enzyme nitrogenase for biological nitrogen fixation, lightning would have been the primary natural process, converting inert nitrogen gas into reactive forms that could be used by the earliest life forms. Some researchers have suggested that lightning-fixed nitrogen, dissolved in rainwater and deposited in the primordial oceans, was a crucial nutrient that supported the earliest ecosystems and helped drive the evolution of life. Thunderstorms also play a role in the global oxygen cycle. The oxygen we breathe was produced over billions of years by photosynthetic organisms, first the cyanobacteria, then the algae, then the land plants. The oxygen cycle today involves a balance between the production of oxygen by photosynthesis and its consumption by respiration, by decay, and by chemical reactions with reduced substances in the Earth's crust. This balance is maintained on timescales of millions of years, and it keeps the atmospheric oxygen concentration remarkably stable at about 21%. Thunderstorms contribute to the oxygen cycle by producing and destroying ozone, which is a reactive form of oxygen. The ozone budget of the troposphere, the balance between ozone production and destruction, is directly influenced by the nitrogen oxides produced by lightning. And the hydroxyl radical, produced in part through the chemistry initiated by lightning, participates in the oxidation reactions that consume reduced gases and transfer electrons to oxygen, maintaining the redox balance of the atmosphere. The role of thunderstorms in maintaining the global atmospheric balance extends beyond nitrogen and oxygen. Thunderstorms are significant players in the global water cycle, transporting water vapor from the surface to the upper troposphere and producing precipitation that returns water to the surface. They are important for the global energy budget, transporting latent heat from the warm surface to the cold upper atmosphere and radiating it to space. And they are important for the global distribution of trace gases and aerosols, mixing the atmosphere vertically and horizontally, and connecting the chemistry of distant regions through the transport of air masses. Consider the connection between thunderstorms and climate, which is a subject of active research and considerable complexity. Thunderstorms affect climate through several pathways. They transport water vapor to the upper troposphere, where it is a potent greenhouse gas. They produce ozone in the upper troposphere, where it is also a greenhouse gas with a particularly strong warming effect. They produce cirrus clouds in their anvil outflow, thin, wispy clouds of ice crystals that both reflect incoming sunlight, which cools the surface, and trap outgoing infrared radiation, which warms it. The net radiative effect of thunderstorm-produced cirrus is still debated, but most studies suggest a slight warming effect. As the climate warms due to increasing greenhouse gas concentrations, the frequency and intensity of thunderstorms are expected to change. Warmer temperatures mean more water vapor in the atmosphere, which provides more fuel for convection and potentially more intense storms. But warmer temperatures also change the stability of the atmosphere in complex ways, and the net effect on thunderstorm frequency is uncertain. If thunderstorms become more frequent or more intense, they will produce more lightning, more nitrogen oxides, more ozone, and more hydroxyl radicals, which will in turn affect the lifetimes of greenhouse gases and the climate itself. This is one of the many feedback loops that make climate prediction so challenging and so important. And then there is the role of thunderstorms in the deep history of the Earth. We mentioned that lightning may have been a primary source of fixed nitrogen in the early atmosphere, but there is an even more speculative and tantalizing idea, that lightning may have played a role in the origin of life itself. In the 1950s, Stanley Miller and Harold Urey conducted a famous experiment in which they passed electrical sparks simulating lightning through a mixture of gases thought to represent the early Earth's atmosphere. The sparks produced amino acids, the building blocks of proteins, and other organic molecules. This experiment demonstrated that the energy of lightning could drive the synthesis of complex organic molecules from simple inorganic gases, and it suggested that lightning-driven chemistry in the early atmosphere might have produced the raw materials from which life emerged. The Miller-Urey experiment has been repeated many times with different gas mixtures and different energy sources, and the results have consistently shown that electrical discharges can produce a wide variety of biologically relevant molecules. While the origin of life is still one of the great unsolved mysteries of science, lightning remains a plausible contributor to the prebiotic chemistry that may have set the stage for life on Earth. This is the grand story of thunderstorms. They are not merely weather events. They are not merely spectacles of light and sound. They are chemical engines, planetary-scale machines driven by the sun's energy, fueled by the ocean's water, and powered by the immense forces of convection and electricity. They are part of the deep machinery of the Earth system, recycling essential elements, regulating the composition of the atmosphere, and sustaining the conditions for life. And they have been doing this work, quietly and steadily, for as long as the Earth has had an atmosphere, long before there were people to watch them, long before there were eyes to see the lightning or ears to hear the thunder. The storms were there, doing their chemistry, shaping the air, tending the atmosphere like patient, tireless gardeners tending a vast and invisible garden. Let that thought carry you gently for a moment. The storms are always working, the chemistry never stops. And the atmosphere, that thin, precious, miraculous shell of gas that wraps around our world and makes everything possible, is always being renewed. Now let us travel even farther. Let us leave the Earth behind gently, the way you might release a balloon and watch it drift upward into the sky and visit the storms of other worlds. Because thunderstorms are not unique to our planet. Wherever there is an atmosphere, wherever there are temperature gradients and convective motions and the potential for electrical charging, there is the possibility of lightning and the chemistry it produces. And across our solar system, and perhaps across the galaxy, storms rage on worlds very different from our own. Let us begin with Jupiter, the giant of our solar system. Jupiter is a world unlike anything in our everyday experience. It has no solid surface. Its atmosphere is a vast, turbulent ocean of hydrogen and helium gas that extends thousands of kilometers deep, gradually increasing in pressure and temperature until the hydrogen becomes a liquid and then a metallic fluid at the planet's core. The atmosphere also contains smaller amounts of methane, ammonia, water vapor, hydrogen sulfide, and traces of more exotic compounds like phosphine and germane. Jupiter's atmosphere is riven by storms of almost unimaginable scale. The Great Red Spot, a storm that has been observed for at least 350 years, is an anticyclonic vortex larger than the Earth itself. Winds within the spot reach speeds of several hundred kilometers per hour, and throughout Jupiter's atmosphere, smaller storms erupt, merge, and dissipate in a continuous, roiling process of convective activity. Lightning on Jupiter was first detected by the Voyager spacecraft in 1979 and has been studied in greater detail by the Galileo and Juno missions. Jovian lightning is extraordinary. Individual flashes have been estimated to release as much as 1 billion joules of energy, roughly 1,000 times more energetic than a typical lightning flash on Earth. The lightning occurs primarily in the water cloud layer, about 50 to 70 kilometers below the visible cloud tops, where temperatures and pressures are roughly similar to those in Earth's thunderstorms, and where the same ice-water charge separation mechanism is thought to operate. The chemistry of Jovian lightning is very different from the chemistry of lightning on Earth because the atmospheric composition is so different. On Jupiter, the lightning channel heats a mixture dominated by hydrogen and helium, with smaller amounts of methane, ammonia, and water. In this hydrogen-rich environment, the high-temperature chemistry produces different products than on Earth. Instead of the nitrogen oxides that dominate Earth's lightning chemistry, Jovian lightning is thought to produce complex organic molecules, hydrocarbons, including acetylene and ethane, and possibly nitriles like hydrogen cyanide formed from the recombination of carbon, hydrogen, and nitrogen atoms in the cooling plasma. These organic molecules may contribute to the complex photochemistry of Jupiter's upper atmosphere, where they are further processed by ultraviolet radiation from the sun. The characteristic brown and orange and red colors of Jupiter's cloud bands are thought to be produced, in part, by complex organic chromophores, colored molecules created by this atmospheric chemistry. Lightning, by generating reactive carbon and nitrogen species in the deep atmosphere, may be one of the sources of these chromophores. Saturn, Jupiter's slightly smaller sibling, also has an active and fascinating atmosphere. Saturn's atmosphere is similar in composition to Jupiter's, mostly hydrogen and helium, with smaller amounts of methane, ammonia, and water. But its storms are different in character. Saturn's atmosphere is generally calmer than Jupiter's, with fewer visible storm systems. But periodically, roughly once every 20 to 30 Earth years, Saturn erupts in a massive storm event called a Great White Spot, an enormous convective disturbance that grows rapidly, encircles the planet, and persists for months before gradually dissipating. The most recent Great White Spot occurred in late 2010, and it was observed in unprecedented detail by the Cassini spacecraft. This storm was a convective monster, producing lightning at rates comparable to the most intense thunderstorms on Earth, with flash rates of several per second. The energy released by the storm visibly altered the thermal structure and chemical composition of Saturn's stratosphere. The lightning in this storm was detected by Cassini's radio and plasma wave instrument as bursts of radio static, each burst corresponding to a lightning flash deep within the ammonia ice clouds. The chemistry produced by lightning on Saturn would be similar to that on Jupiter, the formation of complex organic molecules from the recombination of atoms freed by the extreme temperatures of the lightning channel. Saturn's atmosphere also contains phosphine, a molecule of phosphorus and hydrogen, which is thought to be produced by thermochemical reactions deep in the atmosphere and transported upward by convection. Lightning may play a role in the chemistry of phosphine and its oxidation products, though the details are not well understood. Let us drift now to Venus, our nearest planetary neighbor in the inner solar system. Venus is a world of extremes, a hellish place by any human standard, and yet, in its own way, beautiful and scientifically fascinating. Its atmosphere is thick and dense, composed almost entirely of carbon dioxide, with clouds not of water, but of sulfuric acid, tiny droplets of concentrated sulfuric acid floating at altitudes of 50 to 70 kilometers above the surface. The surface temperature is roughly 460 degrees Celsius, hot enough to melt lead and zinc, maintained by a runaway greenhouse effect. The atmospheric pressure at the surface is about 90 times that of Earth, equivalent to the pressure at a depth of 900 meters in Earth's oceans. Lightning on Venus has been a subject of scientific debate for decades. Several spacecraft, including the Soviet Venera missions and the European Venus Express, have detected radio signals and optical flashes that may indicate lightning in Venus's sulfuric acid clouds. But the evidence is not conclusive, and some scientists argue that the observed signals could have other explanations. If lightning does occur on Venus, it would be unlike any lightning on Earth. The discharge would occur in an atmosphere of carbon dioxide and nitrogen through clouds of sulfuric acid. The chemistry produced would involve the dissociation and recombination of carbon dioxide, sulfur compounds, and nitrogen, potentially producing carbon monoxide, sulfur trioxide, and nitrogen oxides. These products would be unique to Venus's exotic atmospheric environment. Now let us travel farther out to the cold, distant realm of the outer solar system and visit one of the most intriguing worlds known to science, Titan, the largest moon of Saturn. Titan is a remarkable place. It is the only moon in the solar system with a substantial atmosphere, an atmosphere thicker than Earth's, in fact, with a surface pressure about 1.5 times that of Earth. Titan's atmosphere is composed primarily of nitrogen, about 95%, with about 5% methane, and small amounts of other hydrocarbons and nitriles. The temperature at Titan's surface is about minus 180 degrees Celsius, cold enough that methane, a gas on Earth, exists on Titan as a liquid, forming lakes and seas and rain, much as water does on Earth. The chemistry of Titan's atmosphere is extraordinarily complex and beautiful. Ultraviolet light from the distant sun, much weaker at Titan's distance than at Earth's, breaks apart nitrogen and methane molecules in the upper atmosphere. The fragments recombine in a vast cascade of reactions, producing a bewildering variety of organic molecules: ethane, propane, acetylene, hydrogen cyanide, cyanoacetylene, benzene, and many others. These molecules gradually accumulate and polymerize, forming larger and larger molecules that eventually condense into tiny particles of organic haze, a thick, orange-brown smog that blankets the entire moon and gives it its distinctive color. This organic haze, composed of molecules called tholins, rains down continuously onto Titan's surface, where it accumulates over geological time. Titan's surface is coated in a layer of organic sediment, the complex mixture of hydrocarbons and nitriles, and the lakes and seas of liquid methane and ethane are thought to contain dissolved organic compounds as well. If lightning occurs on Titan, and there is some evidence from the Huygens probe and from Cassini observations that it would drive additional chemistry in this nitrogen-methane atmosphere. The extreme temperatures of a lightning channel on Titan could produce hydrogen cyanide, acetylene, ethylene, and other reactive molecules in quantities that would supplement the slower photochemistry driven by ultraviolet light. Some researchers have suggested that lightning on Titan could produce prebiotic molecules similar to those that may have preceded the origin of life on Earth, making Titan a kind of natural laboratory for studying the chemistry that might lead to life under very different conditions. Let us drift even farther now, beyond our solar system, into the realm of exoplanets, planets orbiting other stars. In the past 2 decades, astronomers have discovered thousands of exoplanets, and the diversity of these worlds is staggering. There are hot Jupiters, gas giant planets orbiting so close to their parent stars that their surface temperatures exceed 1,000 degrees Celsius. There are super-Earths, rocky planets larger than Earth but smaller than Neptune, with compositions and atmospheres that remain largely mysterious. There are planets in the habitable zone, the region around a star where liquid water could exist on the surface that may have atmospheres and climates broadly similar to Earth's. On many of these worlds, the conditions for thunderstorms and lightning may exist. Temperature gradients, convective motions, and cloud formation are common features of planetary atmospheres wherever there is sufficient energy and atmospheric mass. Gas giant exoplanets are expected to have vigorous convective storms, with lightning discharges potentially visible from space. Rocky exoplanets with thick atmospheres may have thunderstorms of various kinds, depending on the composition of their clouds, water clouds, sulfuric acid clouds, or perhaps clouds of silicates or iron droplets on the hottest worlds. The chemistry produced by lightning on these distant worlds would depend entirely on the composition of their atmospheres. On a water world with an atmosphere of nitrogen and water vapor, lightning chemistry might resemble Earth's. On a world with a hydrogen-helium atmosphere, it might resemble Jupiter's. On a world with an atmosphere of carbon dioxide and sulfur dioxide, it might resemble what we imagine for Venus. And on worlds with truly exotic atmospheres of silicate, vapor, or iron compounds, the lightning chemistry would produce molecules and minerals that we can barely imagine. There is something deeply calming about this thought. The chemistry we have been exploring tonight, the nitrogen fixation, the ozone production, the radical chemistry, the rain is not unique to our small blue planet. It is a universal process, a consequence of the fundamental laws of physics and chemistry that apply everywhere in the universe. Wherever there is an atmosphere, wherever there is energy, wherever there are atoms that can combine and recombine, the same kinds of chemistry can occur. The details change, the molecules are different, the temperatures are different, the products are different, but the principles are the same. And somewhere out there, on a world we have not yet discovered, orbiting a star we have not yet named, a storm is forming in an alien sky. Lightning is flashing through clouds of unknown composition. Molecules are being created that have never existed before, at least not in that particular combination on that particular world. And the atmosphere of that distant planet is being slowly, quietly, chemically transformed, just as Earth's atmosphere is transformed by every thunderstorm that rolls across our sky. Let your mind drift among the stars for a moment. Let the vastness of it all settle over you like a warm, soft blanket. The universe is full of storms, full of chemistry, full of quiet, invisible processes working patiently, endlessly, on scales that humble the imagination. And yet here you are, warm and safe, resting in the gentle dark, listening to the story of it all. How remarkable and how beautiful that is. A mind born of the same atoms that thunder through alien skies, contemplating the chemistry of the cosmos while drifting toward sleep. And now, the storm is ending. The clouds are breaking apart. They are dissolving back into the sky from which they came, the water within them evaporating, the ice sublimating, the tiny droplets and crystals returning to their invisible gaseous form. The cloud that was once a towering cumulonimbus, a great dark monument of moisture and energy and chemistry, is now a scattering of thin, ragged fragments, drifting apart in the gentle upper-level winds. In an hour or two, there will be nothing left, just clear sky, just stars. The last traces of rain are evaporating from the ground. The puddles are shrinking. The leaves are drying. The moisture is returning to the atmosphere as water vapor, rising invisibly from every wet surface, beginning the cycle once more. The water that fell as rain tonight will, in time, be evaporated, lifted, condensed, and rained out again. The cycle has no beginning and no end. It simply continues endlessly, the same molecules of water participating in storm after storm after storm across the centuries and the millennia. Inside the fading cloud, the chemistry is winding down. The updrafts that powered the storm have weakened and ceased. Without the supply of warm, moist air from below, the cloud has lost its energy source. The ice crystals in the upper levels are sublimating directly into vapor, and the cloud is becoming thinner, more transparent, more ghost-like. The charge that built up inside the cloud over the course of the storm has been discharged by lightning, by the slow leakage of charge through the weak conductivity of the air, and by the settling of charged precipitation. The electrical field is collapsing. The potential for further lightning has faded to nothing. The nitrogen oxides produced by the storm's lightning are dispersing into the surrounding air, carried outward by the gentle spreading of the storm's remnants. Some of these molecules have already been converted to nitric acid and removed from the atmosphere by the rain that fell during the storm. Others are drifting on the night breeze, slowly reacting with ozone, slowly being processed by the nighttime chemistry of the nitrate radical, slowly being converted to forms that will eventually be washed out by a future rain or deposited on a leaf or a field or a body of water. In a day or two, there will be no measurable trace of these molecules. They will have been fully processed and dispersed, their atoms incorporated into other molecules, their energy dissipated, their chemical identity erased. The atmosphere will have returned to its pre-storm state, or rather, to a state so close to its pre-storm state that no instrument could detect the difference. The storm's chemical fingerprint, once vivid and distinct, will have faded completely, like a footprint on a sandy beach washed away by the tide. The ozone that was enhanced by the storm is also returning to normal. The burst of production driven by the lightning-generated nitrogen oxides has tapered off. The ozone is being consumed by its usual reactions with the hydroxyl radical during the day, with the nitrate radical and nitrogen monoxide at night. The pulse of ozone is diffusing outward, thinning, weakening, merging with the background ozone of the atmosphere. In a week, it will be indistinguishable from the ozone that was there before the storm. On the ground, the rainwater is doing its quiet work. It is soaking into the soil, carrying its dissolved cargo of nitrogen compounds, sulfate, bicarbonate, and trace metals downward to the roots of plants and the microorganisms that inhabit the soil. The nitrogen delivered by the rain, the nitrogen that was once a molecule of gas in the atmosphere, that was torn apart by lightning, that was converted to nitric acid, that dissolved in a raindrop, and that fell to earth is now being taken up by a root hair, transported through the vascular system of a plant, and incorporated into an amino acid, a protein, a leaf, a flower, a seed. The storm's chemistry has become the chemistry of life. In a forest, the rain-delivered nitrogen nourishes the soil fungi that partner with tree roots, helping them access nutrients in the soil. In a field, it fertilizes the crops, contributing imperceptibly to the growth of wheat or corn or rice that will eventually feed someone. In the ocean, it feeds the phytoplankton, the tiny, drifting plants of the sea that produce half the oxygen on Earth and form the base of the marine food web. The air smells clean tonight. That characteristic post-storm freshness is the result of everything we have discussed. The rain has washed away dust and particles and pollutant gases. The ozone, carried down from the storm by descending air currents, contributes a faint, sharp note. The volatile organic compounds released from the soil by the impact of the rain, the molecules that produce the scent called petrichor, add an earthy warmth. And the simple absence of the particles that normally scatter light and dull the air makes everything seem sharper, clearer, more vivid. Above, the sky is clearing. Stars are appearing, one by one, then in dozens, then in hundreds. The Milky Way stretches across the sky, a river of light so vast that the mind cannot quite grasp it. Our atmosphere stretches upward into the darkness between us and those stars. Layer upon layer of invisible gas, each layer with its own temperature, its own pressure, its own chemistry. Nitrogen drifts silently, oxygen waits to react, water vapor rises and falls. Ozone forms and breaks apart. The hydroxyl radical flickers in and out of existence, cleaning the air with each brief life. The nitrate radical works patiently in the dark. All of it continuous, all of it quiet, all of it essential. The atmosphere is never still. It is always working, always reacting, always adjusting, always renewing itself. And the thunderstorms that roll across its surface, magnificent, powerful, fleeting, are part of that renewal, part of the great chemical engine that keeps the air breathable, the climate habitable, and the cycles of life in motion. And somewhere, far away across the curve of the earth, another storm is forming right now. The sun, which set hours ago over our quiet sky, is shining on a distant ocean, warming the water, evaporating moisture, seeding the atmosphere with the water vapor that will become the next cloud, the next storm, the next flash of lightning, the next pulse of chemistry. The cycle never stops. The engine never rests. This is the atmospheric chemistry of thunderstorms, a story of invisible molecules and invisible reactions, of immense energies channeled through channels thinner than your finger, of a planetary system so complex and so finely balanced that it has sustained life for nearly 4 billion years. It is a story that plays out above our heads every day, unnoticed and unappreciated by most of the people living beneath it. But it is one of the most beautiful, one of the most elegant, one of the most awe-inspiring stories in all of science. And tonight, you have heard a part of it. Whether you listened to every word, or whether you drifted off somewhere in the middle, carried away by the sound of the rain or the quiet rhythm of the narration, the story is there, floating somewhere in your mind, like a cloud. And the next time you see a thunderstorm, perhaps you will remember something from tonight. Perhaps you will think of the nitrogen being fixed by lightning, or the ozone being produced and destroyed, or the tiny cloud droplets, each one a chemical reactor, floating in the mist, or the rain, carrying its dissolved cargo of acids and nutrients from the sky to the earth. Or perhaps you will simply notice how clean the air smells after the storm has passed, and you will smile, knowing that the chemistry of the atmosphere has done its quiet, patient, extraordinary work once again. The storm has passed. The sky is clear. The molecules are settling back into balance. And you, wherever you are safe and warm and resting. Let the quiet of the atmosphere wrap around you now. Let the slow, patient chemistry of the night carry you gently, gently into sleep. There is nothing more to do, nowhere to be, no molecules to count, no reactions to remember, just the quiet sky above, and the steady, ancient, beautiful work of the atmosphere, continuing as it always has, and as it always will. Good night.